Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into one of the most gently perplexing questions you could ever ask. What was nothing before the Big Bang? But before you self-love, if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the curious corners of existence together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. Imagine, for a moment, the night before anything existed, not just before your birth or before the dinosaurs roamed the earth, but before time had begun, before space had stretched into its vast openness, before matter, energy, light, or dark had a name, or even a reason to exist. What was that like? What could it possibly mean for nothing to be there before anything could be? This isn't just a science question. It's a whisper of a thought that has lived quietly in the back of human minds for as long as we've looked up at the stars and wondered where the trail of before finally ends. Tonight, we're not going to solve it. That's not our goal. Instead, we're going to walk gently around its edges, like tiptoeing around a pond in the fog, tracing the shape of something so vast, so strange, that even our best instruments can only guess at its form. It's a strange thing, really, to ask about nothing. We tend to picture it as an empty room, maybe a dark sky without stars, or a silence so complete it feels like velvet. But even those are something. An empty room has space. A dark sky still contains the possibility of light. And silence? That requires time to unfold. Real nothing, if it even makes sense to call it that, is the absence of all of it. No time, no space, no matter, no energy, not even the rules that govern how things work. And yet, somehow, from that nothing, everything appeared. The stars, the galaxies, the atoms in your teacup, the laughter you shared earlier, and the gentle rhythm of your breath right now. It all began, somehow, from what may have been nothing at all. The question we're exploring tonight, what came before the Big Bang, is like asking what lies north of the North Pole. It seems perfectly reasonable to ask, but the closer you get to the center of it, the more your compass starts spinning. Because time itself, the flowing stream we use to mark change, began with the Big Bang. So how can anything come before time? This question has challenged physicists, philosophers, poets, and everyday dreamers alike. It's a question about origins, but also about the limits of understanding. It's a question about beginnings and also about the edge where science blurs softly into something more like wonder. And tonight, we'll take our time with it. We'll explore what modern cosmology has to say about the Big Bang. We'll visit theories about quantum vacuums and eternal inflation. We'll ask what nothing might really mean and why our minds are so ill-equipped to grasp it. And above all, we'll let ourselves rest inside the question rather than racing toward any final answer. Confiscated to your eyes start to close. That's fine. You're not missing the point. You are the point. A quiet mind, floating gently through curiosity. A traveller wandering softly toward the edges of knowing and finding peace in the quiet not knowing. We'll begin soon with what we do know about the Big Bang. But for now, just breathe. The stars will wait. Let's begin where the story usually starts, 13.8 billion years ago. But even that is misleading, isn't it? Because when we say ago, we're already assuming there's a timeline stretched out behind us, a long ribbon of moments we can trace backward. The Big Bang wasn't just the beginning of the universe, it was the beginning of time itself. So imagine you're standing at the very first second, at the doorstep of what physicists call the cosmic dawn. You look back, and there's no before to look into. Not even darkness, not even stillness, just a kind of blank that isn't empty, it's undefined. This is where science starts to tiptoe. The Big Bang Theory, which has been the most successful model in cosmology for decades, doesn't describe the origin of the universe in the sense of what came before. It describes how space and time, as we understand them, unfolded from an unimaginably dense and hot state. From a point, or perhaps a field, so compact that the laws of physics as we know them simply didn't apply. Submerged in not an explosion in space, it's the expansion of space itself. Everywhere you look in the universe, galaxies are moving away from each other, not because they're flying through space like cosmic debris, but because the space between them is stretching. It's as if the universe is a loaf of rising dough, and the raisins inside, the galaxies, are drifting apart as the dough itself expands. If you ran that process backward in time, everything gets closer, denser, hotter, until eventually you arrive at a singularity, a theoretical point of infinite density, infinite temperature, and zero volume. But even that image is just a placeholder, a metaphor, a shrug in the language of physics. Because when we try to describe that first moment, we run out of words. Not because we aren't clever enough, but because the very concepts we use to make sense of things, distance, size, time, movement, break down at that edge. Still, we try. We say the universe began as a singularity, but that's like describing the birth of a song by pointing to a single note. It gives you something, yes, but not the full feeling of melody. Some scientists argue the singularity never really existed, not as a thing you could point to. Instead, what we call the Big Bang was the beginning of the observable universe, but not necessarily the beginning of everything that could be. Others propose that the early universe wasn't born from a dot, but from a field, a kind of shimmering potential that snapped into being, or shifted its state, creating space and time as a side effect. This has our enormous ideas, and we'll explore them more soon. But for now, just let this image rest in your mind like a soft thought. The Big Bang didn't happen within anything. It was the moment that everything else, distance, matter, hours and minutes, began to unfold. That's what makes the question of before so slippery. You can't step outside time to measure what led to its own beginning. You can't peek around the curtain when the curtain is the stage. And yet, we ask anyway, because it's what we do. We ask where the light came from. We ask what ignited the spark. We ask what nothing is, and whether it ever truly was. And in asking, even if we don't get answers, we find meaning. Not always the kind you can write down on a chalkboard, but the kind that hums softly in the back of your thoughts when the night is still. So as we drift gently onward, keep that hum with you, a quiet, curious echo of a beginning that had no before, but somehow became everything. Next, we'll explore what physicists mean when they say nothing, and why it might be stranger and fuller than you'd ever expect. Let's pause for a moment and think about a word we use all the time but almost never examine. Nothing. Nothing's like it's no big deal. Pilgrimage. What are you thinking about? Subjected, oh, nothing. What's in the box? Nothing. Unfinished before the Big Bang? And nothing? But when we actually try to define it, really define it, things get tangled fast. You might imagine nothing as a kind of empty space, a blank canvas, a silent room with the lights turned off and no furniture. But even that isn't truly nothing. That room has space, it exists in time. There's still a where and a when, and perhaps even an expectation that something could walk through the door at any moment. Real nothing, if such a thing can exist at all, is the absence of everything. No matter, no light, no space, no time, not even the laws that tell things how to behave, not even the expectation that something might come next. And that kind of nothing is almost impossible to imagine. It's not our fault. We are creatures built to notice things, patterns, textures, the curve of a shadow on a wall. Even when we close our eyes, our minds fill the darkness with floating thoughts and flickering lights behind the eyelids. We are wired to fill space, not to sit inside perfect absence. That's why, when physicists talk about nothing, they often don't mean nothing in the philosophical sense. They're usually referring to something more technical, more precise, and, in a strange way, more full. Let's take quantum field theory as an example. According to this deeply successful branch of modern physics, even what we might call empty space isn't really empty. Instead, it's a bubbling broth of energy, fluctuating fields and virtual particles that pop in and out of existence faster than we can catch them. Terminated, this is sometimes called the quantum vacuum, and it's a far cry from the absolute silence of nothingness. Fields like the electromagnetic field or the Higgs field are still present, even if nothing else seems to be. These fields are like invisible fabrics stretched across the universe. Even when there are no particles, no photons, no electrons, these fields still exist, quietly waiting, still capable of being stirred. Abolish and they do get stirred. Quantum fluctuations, tiny, unpredictable ripples in these fields can cause particles to appear spontaneously. Live, brief, flickering lives, and vanish again. This isn't a fantasy or a loophole, it's been measured, observed, and verified in laboratories. In fact, the very fact that atoms don't collapse in on themselves depends on these rules. So in quantum physics, nothing is more like a restless silence, a fertile void, a sea of possibility. Bernstein is why some scientists, like physicist Lawrence Krauss, have argued that the universe could arise from nothing if you're willing to accept this quantum version of nothing as your starting point. In that model, the laws of physics are already baked into the background. The quantum vacuum exists, and given enough time, or maybe just enough inevitability, a universe can emerge. It sounds elegant, almost hopeful. But critics of that idea point out that it's not really nothing if laws still apply. If you have fields and potential and time in which to wait for fluctuations, you don't have a true void. You have something, a subtle, mathematical something, but something nonetheless. Still, even that version of nothing is difficult enough for the human brain to wrap itself around. It's not a place, it's not a moment, it's not even a question of cause and effect in the traditional sense. It's more like a whisper in a language that no one remembers how to speak. Inversion of nothing, and version of nothing's long to share. But for now, let this sit with you. Perhaps the deepest mystery isn't that something came from nothing, but that we can imagine nothing at all. At the heart of everything we see, feel, and are lies a moment. A moment that wasn't really a moment at all, not in the ordinary sense. It didn't happen in time or at a place. Instead, it was the beginning of both. Time and space didn't stretch out to welcome it, they emerged from it. This idea, what we call the Big Bang, isn't just the opening act in a cosmic play. It's the stage, the script, and the first note of a universe-sized symphony that still plays around and within you. But let's be gentle here. The name Big Bang can be a bit misleading. It is an enormous explosion flinging stars and galaxies outward from some central point, like a firework in the sky, with debris and brightness and noise. But the reality, as physicists understand it, is far quieter and far stranger. There was no centre, no surrounding space for the universe to explode into, no outer edge from which to look in. The Big Bang wasn't an event happening in space. It was the expansion of space itself. Prejudice didn't send expansion, didn't send matter flying through the cosmos like shrapnel. It carried space along with it, like raisin bread rising in the oven. Every raisin, every galaxy moves away from the others, not because it's travelling on its own, but because the dough between them is swelling. That's what scientists like from distant galaxies. They're not just moving, they're being carried by the expansion of space itself. The further away they are, the faster they seem to recede. This was first noticed by Edwin Hubble in the 1920s when he studied the faint glow of galaxies and found that their light was stretched, redshifted, by motion. And from that clue, along with the cosmic microwave background, the faint afterglow of the early universe, we've pieced together a surprisingly detailed picture of what happened next. But there's a limit. Conserve, even the best telescopes can only look so far back. At some point we hit a wall, not of distance but of clarity, a moment so dense, so hot and so compressed that our equations start to break down. That's the earliest we can currently see, about 380,000 years after the Big Bang. Before that, the universe was too opaque, too chaotic for light to travel freely. And even further back, at the very beginning itself, we hit what physicists call a singularity. Now, singularity doesn't mean a sharp dot in space, it means a breakdown in our understanding, a point where our current models, including Einstein's general relativity, just don't work anymore. It's a signpost that says, "Here be dragons," or at least unknown physics. So what do we actually know about the Big Bang? We know the universe is expanding. We know that in the past it was hotter and denser. We know that light, atoms and galaxies came later in a long unfolding dance of cooling, clustering and forming. We can trace the fingerprints of that process in the background radiation and in the chemical makeup of stars. What we don't know yet is what happened in those first moments, or if moments is even the right word. The earliest fractions of a second, fractions of fractions, are still cloaked in mystery. Did the universe emerge from a quantum fluctuation? Was it the result of a collapsing star in another universe? Was it the bounce of a cycle that repeats forever? Breaches, and we'll wander through some of them gently in the sessions to come. But for now, it's enough to say, the Big Bang wasn't a bang, loud, it wasn't bright, and it wasn't something you could have stood outside of to watch. It was the beginning of everything, including the tools we use to understand it. So when we ask what happened then, we're also asking how we know anything happened at all, and how far human minds and hearts and telescopes can reach into the past. Soon, we'll explore what exactly began at that origin point, and what that tells us about space, time, and the rules that seem to govern reality. If you close your eyes for a moment and imagine the beginning of the universe, you might picture a great flash, a bang. A sudden moment where silence broke and the world began. But what began, exactly? That question, as soft as a whisper in the dark, is what we'll gently explore tonight. The Big Bang wasn't an explosion in space. It was the origin of space itself. It wasn't a spark within time. It was the emergence of time. And that's where things begin to feel strange. Because we're so used to beginnings having a before, a time, a place, a reason. That had no stage to perform on, no ticking clock to count its first beat. It created the very possibility of clocks. So when cosmologists speak of the Big Bang, they don't mean a blast echoing through empty air. They mean a moment, if we can even call it that, when the fabric of reality unfurled from a state of unimaginable density into something larger, cooler, more structured. Privileged from that first unfolding, three things bloomed into existence together: space, time, and the laws of physics. Let's start with space. Before the Big Bang, there wasn't a void waiting to be filled. There was no container, no background, no out there. Space itself began stretching, like a sheet that hadn't existed a moment before. And this wasn't expansion into anything else. It was space growing into itself. Every point in the universe, no matter how far apart now, was once pressed together, not in one location, but as one reality. Next came time, or rather, time started, not with a clock or a rhythm, but with the first potential for change. Time, in the language of Einstein, is woven together with space into something called space-time, a smooth, bendable geometry that defines what can happen and when. Without space-time, there's no before and after, no cause and effect, no memories, no unfolding. So to ask what happened before the Big Bang may be as confused as asking what lies north of the North Pole. The question assumes a direction that doesn't exist. And then, the rules. Springfield of physics weren't simply waiting for the curtain to rise. They may have crystallized out of that original state, like frost forming on glass. Gradually, subtly, but profoundly. At first, the universe may have been governed by a single, unified force. No gravity, no electromagnetism, no contrast. Just raw, undivided energy. Verse expanded and cooled, that symmetry broke. Gravity peeled away first, giving the universe structure. Then the strong and weak nuclear forces diverged. Eventually, light itself emerged, and the universe began to glow. These separations weren't chaotic, they were elegant transitions. At the Big Bang, then, wasn't just matter. It was possibility, a stage, a script, and a clock. A way for something to become something else. No one knows for certain whether this was truly the beginning of everything, or just the beginning of our branch of the story. But we do know that with the birth of space, time, and law, the conditions for change were set in motion. This joint is possible, everything else becomes possible too. In our next session, we'll gently clear away some of the common mental pictures people have about the Big Bang. Because while it's often described as a blast or a fireball, the truth, as usual, is quieter and far more strange. If you close your eyes for a moment and imagine the beginning of the universe, you might picture a great flash, a bang. A sudden moment where silence broke and the world began. But what began, exactly? That question, as soft as a whisper in the dark, is what we'll gently explore tonight. The Big Bang wasn't an explosion in space. It was the origin of space itself. It wasn't a spark within time. It was the emergence of time. And that's where things begin to feel strange. Because we're so used to beginnings having a before, a time, a place, a reason. That had no stage to perform on, no ticking clock to count its first beat. It created the very possibility of clocks. So when cosmologists speak of the Big Bang, they don't mean a blast echoing through empty air. They mean a moment, if we can even call it that, when the fabric of reality unfurled from a state of unimaginable density into something larger, cooler, more structured. Privileged from that first unfolding, three things bloomed into existence together: space, time, and the laws of physics. Let's start with space. Before the Big Bang, there wasn't a void waiting to be filled. There was no container, no background, no out there. Space itself began stretching, like a sheet that hadn't existed a moment before. And this wasn't expansion into anything else. It was space growing into itself. Every point in the universe, no matter how far apart now, was once pressed together, not in one location, but as one reality. Next came time, or rather, time started, not with a clock or a rhythm, but with the first potential for change. Time, in the language of Einstein, is woven together with space into something called space-time, a smooth, bendable geometry that defines what can happen and when. Without space-time, there's no before and after, no cause and effect, no memories, no unfolding. So to ask what happened before the Big Bang may be as confused as asking what lies north of the North Pole. The question assumes a direction that doesn't exist. And then, the rules. Springfield of physics weren't simply waiting for the curtain to rise. They may have crystallized out of that original state, like frost forming on glass. Gradually, subtly, but profoundly. At first, the universe may have been governed by a single, unified force. No gravity, no electromagnetism, no contrast. Just raw, undivided energy. Verse expanded and cooled, that symmetry broke. Gravity peeled away first, giving the universe structure. Then the strong and weak nuclear forces diverged. Eventually, light itself emerged, and the universe began to glow. These separations weren't chaotic, they were elegant transitions. At the Big Bang, then, wasn't just matter. It was possibility, a stage, a script, and a clock. A way for something to become something else. No one knows for certain whether this was truly the beginning of everything, or just the beginning of our branch of the story. But we do know that with the birth of space, time, and law, the conditions for change were set in motion. This joint is possible, everything else becomes possible too. In our next session, we'll gently clear away some of the common mental pictures people have about the Big Bang. Because while it's often described as a blast or a fireball, the truth, as usual, is quieter and far more strange. Let's sit for a moment with the name we've given this whole idea. The Big Bang. It sounds dramatic, doesn't it? Loud, explosive, something you'd expect to shake the walls and scatter stars like sparks from a fire. But the truth is, the Big Bang wasn't big. And it wasn't really a bang. Prestige itself was first used in the mid-20th century by astronomer Fred Hoyle, who, curiously, didn't even believe in it. He supported a different idea called the steady-state model and used the term Big Bang almost as a joke, a bit of radio sarcasm. But the name stuck, and now it's become one of the most famous phrases in all of science. Still, it's a little misleading, because it makes us imagine something like a grenade going off in the middle of empty space, energy radiating outward into the darkness. But there was no middle, no outside, no darkness waiting for light to fill it. The Big Bang was not an explosion in space. It was the birth of space itself. And when we say the universe is expanding, we don't mean that galaxies are flying through space like debris from a blast. We mean that the space between galaxies is stretching. Like a balloon being inflated, or dots on rising dough spreading apart, not because they're moving, but because the surface beneath them is growing. This is why every galaxy seems to be moving away from us, not because we're in the centre of some cosmic detonation, but because the expansion happens everywhere at once. There is no special vantage point, no central blast zone, just more and more space, gently stretching like taffy. Even the idea of the Big Bang as a moment can be a little off. In most versions of the theory, the Big Bang isn't something that happened at a point in time, but rather something that defines the beginning of time itself. The early universe didn't detonate and then settle. It expanded, cooled, and slowly became more structured, like a fog lifting or a melody forming from a single note. If you could travel back, not just in distance but in time, you wouldn't see a fireball in the sky. You'd find yourself inside a hot, glowing soup, thick with particles and light. Not a bang, but a bloom. Not a flash, but a becoming. And here's another gentle twist. Even though we call it the beginning, the Big Bang doesn't tell us how the universe came into existence. It describes how it evolved from a very hot, very dense, very uniform state. What happened before that, or whether before even makes sense, is a question we'll explore soon. The point is, our language stumbles a bit when we try to describe these earliest moments. It wasn't a bomb, it wasn't an explosion, and it didn't happen in a place. All of those ideas come from our experience with things inside the universe. But the Big Bang wasn't something in the universe. It was the moment the universe itself began to unfold. Flooring and so, still we use them because we need some way to wrap our minds around the vast and the abstract. And that's okay, as long as we remember they're metaphors, not maps. So if your mental image of the Big Bang is a loud pop echoing through the dark, gently let that go. Replace it with something quieter, sexual, a soft stretch, and breath. A cosmic unfolding, nowhere and everywhere all at once. In our next session, we'll continue tracing that unfolding in slow motion. We'll take a walk through the early moments of the universe's timeline, second by second, as things cooled, expanded, and began to take on shape. But for now, just rest in the idea that what we call the Big Bang was not a bang at all. Let's take a quiet walk through the earliest story the universe ever told. Not in a rush, not all at once, but in slow motion, so we can feel each unfolding moment as it gently happened. Long before planets formed, long before atoms cooled into you. Because for all the mystery that surrounds the beginning of the universe, what comes after that beginning, what comes in the very first seconds, is surprisingly well understood. And that story is told in temperature, in energy, in change. We'll begin at the beginning. At time zero, the universe is hot. Not just stove hot or sun hot, but everything hot. A kind of heat that doesn't just burn, it defines everything. Temperatures so extreme you couldn't even have particles. No protons, no electrons, no atoms, just energy, raw and roiling. Within a tiny, tiny fraction of a second, far less than a blink, this hot, dense state begins to expand. Rapidly. This moment is often called cosmic inflation. The universe doesn't just grow, it inflates. From smaller than a subatomic particle to something the size of a grapefruit, or maybe even bigger. It happens so fast and so thoroughly that the universe becomes smooth, almost perfectly even across vast distances. Then the expansion slows. Not stops, but relaxes, just a little. The inflation phase ends, and the energy trapped in that initial state releases like a breath being exhaled. That release fills the universe with a thick, glowing plasma, a sea of particles and radiation. 1 second after the Big Bang, quarks and gluons, the tiniest known bits of matter, roam free. It's a chaotic soup, a quark-gluon plasma, hotter than any star, denser than any core. But as the universe continues to expand and cool, quarks begin to combine. They form protons and neutrons, the building blocks of atomic nuclei. This happens in the first second. 1 second after the Big Bang, and the basic ingredients of matter are already in motion. By the 3-minute mark, those protons and neutrons begin to stick together. Hydrogen, helium, a dash of lithium. No carbon yet, no oxygen. Just the lightest elements, formed in a brief, delicate window called primordial nucleosynthesis. Chemistry, if we can call it that, has its first breath. But for the next few 100,000 years, light is trapped. The universe is still too hot for atoms to fully form. Every time an electron tries to settle into orbit around a nucleus, a stray photon knocks it away. The universe is a glowing fog, a soft, dense light echoing everywhere. Then, at around 380,000 years, a transformation. The universe cools just enough that electrons can finally settle down and form stable atoms. And when they do, light is freed. For the first time, photons can travel across the cosmos without being bounced around. This light is still light you can see, not from stars, not from galaxies, but from the very moment the universe became transparent, a fossil of the first light. After that, things seem quiet for a while. Gravity slowly begins to pull matter together. Tiny fluctuations, little ripples in the density of the early universe, start to grow. Over millions of years, these ripples become the seeds of galaxies. Stars begin to form. Nuclear furnaces light up the darkness. And inside those stars, heavier elements begin to cook. Carbon, oxygen, iron, the ingredients not just of planets, but of people. Plunged from 1 second to 1 billion years, the story of the universe is one of expansion, cooling, and becoming. From plasma to particles, from particles to atoms, from atoms to light, from light to stars, and eventually to us. It's a slow bloom, not sudden, not violent, just quiet transformations unfolding over time. The next session will look more closely at those earliest ingredients, quarks, light, inflation itself, and how they shape everything that followed. But for now, just let this gentle timeline rest in your thoughts. From heat came order, floppy from simplicity, complexity, and from the void, a sequence of moments that still echoes through your very cells. Let's return for a moment to the very beginning. those first flickers of existence, when the universe was not yet a universe, but a swelling possibility. Afterglow of the cosmic microwave background, the moment light was finally free to roam. But, to fully understand how we got there, we need to pause a little earlier in the timeline. In those first, fleeting slivers of a second, something extraordinary occurred. So fast, we barely have words for it, yet so powerful, it shaped everything that followed. This was the era of inflation. Not economic, not balloon animals, but a moment in which space itself expanded faster than the speed of light. Don't worry, this doesn't break the rules. Objects can't move through space faster than light, but space itself can stretch without limit. Pagamento it did. In less than a trillionth of a second, the universe expanded from a volume smaller than a proton to something the size of a grapefruit, or perhaps even larger. A cosmic growth spurt of unimaginable speed and scale. Did this happen? No one knows for sure. Inflation is a theory, but a well-supported one. It helps explain why the universe looks so smooth in every direction, why its structure is nearly flat, and why even galaxies, billions of light years apart, seem to follow the same early rhythm. Position may have also planted the seeds of everything we now see. Tiny quantum fluctuations, stretched by that rapid expansion, which later became the scaffolding for galaxies, stars, and dust. Little wrinkles, frozen into the fabric of space, that would eventually grow into the grand architecture of the cosmos. But what was the universe made of during this time? Not atoms, not even protons or neutrons. It was filled with quarks, the smallest known building blocks of matter, and gluons, the force carriers that hold them together. First, these particles existed in a kind of glowing chaos, a quark-gluon plasma, where everything was too hot and dense for anything stable to form. Temperatures soared to over 1 trillion degrees Celsius. Matter and antimatter blinked into existence and vanished again, locked in a dance of mutual destruction. It cooled. Unmistakers cooled. Quarks began to combine, 3 at a time, forming protons and neutrons. These combinations were stable, persistent, the first building blocks of the visible world. And light, photons, was everywhere, scattered, absorbed, re-emitted, tangled with matter in a storm of radiance. You couldn't see through it. It wasn't illumination yet. It was a glowing fog with no beginning and no edge. Everything was energy. Everything was motion. But it wasn't random. Even in that chaos, rules were being followed. Rules that emerged, perhaps, in the earliest instant of time. The strong nuclear force, holding quarks together. The electromagnetic force, binding particles and shaping interactions. Gravity, beginning to nudge. Matter ever so slightly together. These weren't accidents. They were the beginning of structure, order, and possibility. Somewhere in this haze of light and heat, the matter that would one day become your body was already present. Not assembled, not even recognizable, but there, in quarks, in protons, in the potential for stars to form, and for those stars to forge the elements of life. The early universe wasn't quiet. It was wild, hot, humming with energy. But it wasn't disorganized either. It was full of rules, newborn, elegant, invisible rules that guided its every motion. And yet, despite all the complexity, it was also profoundly simple. Uniform, smooth and vast. A canvas waiting to be painted by gravity and time. Then light. They may sound like abstract concepts, but they are the first strokes in the story of everything. The first shimmerings of form, the first rhythm of a clock that would never stop ticking. In the next session, we'll ask a question that quietly challenges all of this. What if asking, before the Big Bang, is a meaningless question? What if there truly was no before? But for now, rest in the wonder of a universe that began as a whisper of possibility and became, slowly, you.
Now, here's a question that seems perfectly reasonable, gentle even. What was there before the Big Bang?
But the closer you lean into it, the more it pulls away. Like mist over a pond, the idea of before begins to lose its shape. It vanishes, not because we're not looking hard enough, but because it may not be there at all. We are creatures of time. We wake, eat, walk, grow older. We speak in pasts and futures. Our very thoughts move through sequences, one thing, then another. It feels natural to imagine time as a long road stretching behind us, and of course we'd want to know what lies even further back. But according to modern physics, that road may not have a stretch before the beginning. It may start at the Big Bang, and that's it. No dirt trail behind it, no hidden tunnel, just a horizon you can't step past. Not because it's guarded, but because it simply doesn't exist. To understand why, we have to look at Einstein's theory of general relativity, which tells us something strange. Time is not separate from space. It's not an invisible stream flowing through the universe. It's part of the universe, interwoven, folded, shaped by matter, energy and gravity. The more mass there is in a region, the more time bends. It can stretch, it can slow. And in certain extreme conditions like black holes or the early universe, it can behave in ways that defy common sense. At the Big Bang, the universe was compressed into a state of extraordinary density and heat, so dense in fact that our equations break. Time itself loses meaning. We call this a singularity, not a place, not a moment, but a breakdown in the language of physics. And this is where before becomes tricky. If time is part of the universe, something that emerged with the Big Bang, then asking what came before is like asking what's south of the South Pole. The word before only makes sense inside time. Outside of it, it's a question without a grammar. Of course, our minds still want to know. They reach beyond the line, not because the question is flawed, but because curiosity is the most natural thing we do. Some scientists propose ways to stretch this idea further. One such concept is the no-boundary proposal, developed by Stephen Hawking and James Hartle. In this model, the universe didn't start with a singular edge like a wall or a cliff. Instead, time in the early universe was curved like the surface of a sphere. Think of the Earth's surface. You can walk north until you reach the North Pole, but after that, north loses meaning, not because the map is incomplete, but because you've reached a smooth natural end. In Hawking's idea, the universe may have a similar shape in time, not a sharp beginning, but a rounded one, a time that gently curves in on itself, leaving no edge to fall off, no before to reach. Cyclic universes that expand and contract in endless rhythms, quantum. Let's take a moment to sit with a word so familiar, so ordinary that we rarely notice how strange it really is. Nothing. It's one of the first concepts we learn as children, when the cookie jar is empty, when the toy box has been cleaned out, when someone asks what you're thinking and you quietly murmur, nothing. We use the word so casually, so often. But when you try to press it into shape, when you ask it to hold still and reveal what it really means, it dissolves, displaced, because what is nothing, really? SpaceX, you might picture an empty room, white walls, no furniture, silence, stillness. But the room has size, it takes up space, you can walk across it, breathe its air, feel its temperature. That's not nothing, it's simply emptiness dressed up in familiar surroundings. You might imagine outer space, the vacuum between stars, but that too is something. It has geometry, it has dimensions, it carries radiation, it allows particles to travel through it, even if they rarely do. It's not a complete absence, just a quiet place. And even if you try to picture absolute blackness, you're still picturing something. There's still a viewer in the scene, still a perspective, a point of reference, a you. Precondition, if such a thing exists, would be the absence of everything. No space, Nesday, Noi time, no atoms or fields, no gravity, no up, no down, no rules, no expectation that anything could ever happen, stabilize, don't avoid, not a blank, not a pause between things, just the total absence of being. And suddenly it's hard to keep hold of the idea. Undermined, that's because our minds aren't made to think this way. We evolved in a world full of things, rocks and rivers and voices and light. We understand contrast, motion, change. Even when we close our eyes and try to picture nothing, Our brains fill the space with floating dots of thought, colours behind the eyelids, imagined depth and silence. We cannot truly imagine the absence of context, and that's okay. It's not a failure of intelligence. It's simply a limit of the kind of minds we have. So when physicists and philosophers talk about nothing, they often mean very different things. Philosophers' nothing is radical. It means the complete and total lack of existence, not just of matter but of potential, not just of events, but of the laws that would allow events to occur. It's not a place where something hasn't happened yet. It's the place where nothing could ever happen. Physicists' nothing, on the other hand, tends to be more forgiving. In physics, a vacuum can still have structure. It can have shape, fields, energy, and possibilities. That version of nothing, which we'll explore in coming sessions, might not be truly empty at all. It might be teeming with subtle motion, with fluctuations, with the raw ingredients of something waiting to unfold. This is where science begins to blur into philosophy, where definitions start to matter, where the question, what is nothing, becomes a lens for understanding everything. Because if the universe came from nothing, then what kind of nothing was it? And if there never was nothing, then maybe something has always existed, quietly, patiently, waiting to become this. You, listening now, are part of that something. You are made from matter that was once scattered stardust, and before that energy, and before that, who knows? But even asking the question is an act of wonder, and that wonder is a kind of light flickering into the dark. In the next session, we'll step deeper into this divide between philosophical nothing and the so-called empty space of physics, and we'll find that what we once called nothing may actually be far stranger and far fuller than we ever imagined. So now that we've sat quietly with the word nothing, let's gently stretch it from two sides and see where it begins to bend, because depending on who you ask, nothing can mean very different things. In philosophy, nothing seriously and very literally is the complete absence of being, not just the absence of stuff, but the absence of space, of time, of possibility. It's not darkness, it's not emptiness, it's the absence of the very conditions under which darkness or emptiness could even be imagined. Nothing is as deep as absence can go. No substance, no laws, no stage, not even a direction in which something might begin to appear. It's not that something hasn't happened yet, it's that there's no framework in which anything could ever happen. A silence so total that it swallows the idea of music. Now compare that to the physicist's version of nothing. In physics, particularly in cosmology and quantum mechanics, the word is often used more loosely. Nothing might refer to empty space, a vacuum devoid of matter, but still full of rules, still defined, still humming with structure. And here's where things get strange. Because in modern physics, even the most perfect vacuum completely empty of particles isn't truly empty. It still has fields, invisible, measurable, ever-present fields that stretch across the entire universe. These are not things in space, they are the fabric of space. Thing can still do something, it can ripple, it can fluctuate, it can give rise to virtual particles that appear and vanish in less than a heartbeat. It can carry energy, it can shape the expansion of the cosmos. To a philosopher, this is not nothing at all. It's a subtle kind of something dressed up in emptiness. And that's fair. JFK, because when a physicist says the universe came from nothing, what they often mean is that it came from a vacuum-like state governed by physical laws, a place without matter but not without possibility, a quantum field, a geometry, a stage. And if that's true, if the universe emerged from such a nothing, then the question isn't why did something come from nothing, but rather why do these laws and fields exist in the first place? That question brings us right back to philosophy, because even if physics can explain how a universe can emerge from a quantum vacuum, it can't quite explain why there should be a vacuum to begin with, why the laws of quantum mechanics exist, why anything is here rather than not. That, as philosophers have long said, may be the deepest question of all. So like this, the physicist's nothing is like a blank page, no ink, no letters, no story yet written. But the page itself is still part of the book. The philosophical nothing is what happens if you remove the page, the book, the author, the language, and even the possibility of story. Writing. Our minds struggle to hold on to that second version. But both perspectives are valuable. The physicist's view gives us tools, models, predictions, ideas we can test. The The philosopher's view reminds us that some questions lie deeper than data, and that meaning is not always measurable. And so, we find ourselves floating somewhere in between the vacuum that science can measure and the abyss that reason can barely touch. In the next session, we'll explore what quantum field theory says about this vacuum, that seething, not quite nothing where particles can arise and space is anything but still. It's enough to recognise that nothing is not one thing. Confiscated it is many things. At it, the closer we look begins to feel. Let's step now into the strange heart of physics, where emptiness is never really empty and silence is never truly still. In the world of quantum field theory, the vacuum, the so-called nothing, isn't a blank canvas, it's more like a restless ocean. Even when there are no particles, no atoms, no dust or starlight, the vacuum isn't void. It's alive with invisible energy, fluctuations, and fields that ripple quietly beneath the surface. This isn't just an idea, it's one of the most successful frameworks in all of physics. Quantum field theory, or QFT, underpins our understanding of particles and forces. It describes the world not in terms of billiard ball particles bouncing around, but in terms of fields, invisible, continuous entities that exist everywhere in space. Each particle we know, the electron, the photon, the quark, is just a small ripple in a specific field. The electron is a tiny wave in the electron field. A photon is a flutter in the electromagnetic field. These fields are always present, even when no particles are around. They're woven into the fabric of space itself. And here's where things get truly strange. Even when these fields are at their lowest possible energy, when nothing seems to be happening, they still hum. They never quite rest. This is known as vacuum fluctuation. You could think of it like this. Imagine a perfectly calm pond. No wind, no movement. And yet, if you could look closer, much closer, you'd see tiny ripples on the surface, spontaneous and unpredictable, caused by nothing more than the pond's own restless nature. Banged, that's what the vacuum is like. At the smallest scales, it's never perfectly still. There's always a little motion, little flickers of energy. These fluctuations are a natural consequence of the uncertainty built into quantum mechanics. The rule that says you can't know everything with perfect precision, not even the energy of nothing. Fluctuations mean that, even in empty space, pairs of particles can briefly pop into existence. A particle and its antiparticle borrow a little energy from the vacuum, and then vanish again almost immediately. These are called virtual particles, minimized, not directly observable in the way real particles are, but their effects are very real. They slightly shift the energy levels of atoms, they help explain how forces behave, and in the case of Hawking radiation, they even allow black holes to slowly evaporate over time. Synchronized in a strange, quiet way, nothing, in quantum field theory, is a dance floor that never quite clears. There's always a faint rhythm, a background beat that can never fully be silenced. And perhaps most surprisingly of all, the energy of this quantum vacuum might not be zero. In fact, it could have a small but measurable value, a vacuum energy that affects the expansion of the universe itself. We'll return to that idea in a later session. Just consider what this means. The vacuum, the thing we once thought of as absolute emptiness, is not only something, it's structured, governed by rules, responsive, restless, full of potential, even if it looks like absence. It isn't silence, it's a kind of whisper, and perhaps this whisper was all it took to begin a universe. In the next session, we'll zoom in on these virtual particles, the fleeting ghosts that flicker in and out of existence, and explore how this ephemeral activity might shape the very nature of space and time. But for now, let yourself rest with this gentle thought. Sluggish arts of the cosmos. Something is always stirring. Let's stay for a while in that quiet place, where nothing is truly still, and the fabric of space is always alive with subtle motion. We've talked about quantum fluctuations, those tiny ripples that dance through every quantum field, even in the so-called vacuum. Now let's focus more closely on what those fluctuations give rise to, the strange and fleeting creatures known as virtual particles. These are not particles in the usual sense, not little bits of stuff flying around in space. They're temporary, ephemeral, They flicker into being from the vacuum, last for the briefest breath of time and vanish again before they can be pinned down. A particle and its opposite, a mirror twin called an antiparticle, appear together, then disappear, as if space itself is dreaming of motion. This might sound like a metaphor, but it's more than poetry. It's math. It's built into the equations of quantum field theory. And even though these particles can't be directly observed, their effects have been measured. Precisely. One famous example is the Casimir effect. Imagine placing two metal plates very, very close together in a vacuum, closer than a human hair is wide. In that tiny gap, some wavelengths of these vacuum fluctuations are excluded, while others are allowed. The result? The plates are gently pushed toward each other, not by any visible force, but by the restless pressure of space itself. It's like the vacuum is pressing in from the outside, reminding us it's never really empty. These flickering pairs also play a role in the behavior of atoms. They subtly shift the energy levels of electrons orbiting a nucleus. This is called the Lamb shift, and it was measured with exquisite precision in the 1940s. Another quiet confirmation that the vacuum hums with activity. Now let's zoom in even further, to the very structure of space-time itself. Abortion at the smallest imaginable scales, far smaller than atoms, even smaller than quarks. Physicists believe space may not be smooth at all. It may be frothy, uneven, bubbling. This idea is called quantum foam. By physicist John Wheeler, quantum foam is the idea that, at the Planck scale, the tiniest scale where both gravity and quantum effects must be considered, space-time behaves more like boiling water than a flat table. Little bubbles of curvature rise and collapse. Tiny wormholes may flicker in and out. Space and time themselves become uncertain, shifting, maybe even discontinuous. We don't yet have the tools to directly observe this foam, or even a complete theory that can describe it with certainty. But many physicists believe it's real, or at least that something very strange is happening at that scale. And here's the quiet implication. If the vacuum is full of virtual particles, and if space itself is foamy and shifting at its roots, then even the most silent corner of the universe is a theatre of activity, a constant rehearsal of potential. It's always well to get being the simulative mine. The vacuum remargins. It's not chaotic, it's not loud, but it's not nothing either. It's a low murmur, a background shimmer, a place where the laws of physics continue to operate even in the apparent absence of matter. And perhaps, just perhaps, it's from this seething, structured nothingness that everything else emerged. In the next session, we'll explore the concept of vacuum energy, the measurable energy of empty space, and ask whether this quiet background hum could be enough to create a universe from nothing at all. But for now, let your thoughts drift gently, like particles on a quantum sea. The emptiness is not silent. Reopened, even now, the void may be whispering worlds into being. By now we've spent a good while wandering through what we once thought of as empty space, only to find that it's anything but. In quantum field theory, the vacuum isn't barren. It's more like a field of unending potential, rippling with invisible activity, flickering with virtual particles and textured by subtle laws. But even more than that, this so-called nothing carries something measurable. It has energy. Aphorical energy, real energy. Detectable, calculable, and perhaps cosmologically significant. Skies brings us to one of the strangest ideas in modern physics, vacuum energy. Let's take a quiet step back. In most classical systems, you can define energy in terms of motion or heat or height. A ball at rest on the ground has zero potential energy. Nothing is happening, all is still. Quantum world, stillness isn't allowed. The Heisenberg uncertainty principle ensures that no particle, no field can ever be perfectly at rest. There's always some jitter, some fundamental blur of motion and position. And even in a vacuum, where no particles are present and all fields are at their lowest possible energy, there's still a trace amount of energy left over. That's vacuum energy, and it's everywhere. It's not a glitch in the math, it's baked into the structure of quantum mechanics. Professionalism. So what does this quiet hum actually do? Bathrooms. Turns out quite a bit. First, vacuum energy might help explain the accelerating expansion of the universe. In the late 1990s, two independent teams of astronomers discovered something surprising. Distant galaxies weren't just receding, they were receding faster and faster. The expansion of the universe was speeding up. This went against everything we expected. Gravity should have been slowing things down. Turbulence to account for this acceleration, physicists proposed something called dark energy, a mysterious force that fills all of space and pushes outward. And one possible source for that energy? The vacuum itself. If vacuum energy exerts a kind of pressure on space, it could stretch the cosmos from within, a gentle, persistent expansion driven not by matter or motion, but by the very nature of emptiness. This leads to a provocative idea. Maybe the vacuum isn't just full of energy, maybe that energy can do things. Maybe it can shape the universe. And maybe, just maybe, it can create one. Flooring physicists, including Stephen Hawking and Alexander Vilenkin, have proposed that our universe could have spontaneously emerged from a quantum vacuum, a place with no matter, no time, but still a bubbling energy field governed by quantum laws. In this view, you don't need a creator, a trigger, or an outside cause, just a vacuum, and a bit of statistical inevitability. If the laws of quantum physics apply to the vacuum, and if the vacuum allows for fluctuations, then given enough time or enough possibility, a universe like ours might appear, not as a planned event, but as a natural emergence, like steam rising from a warm surface, or frost forming on cold glass. Of course, this raises a gentle objection. If this vacuum has energy, structure, and laws, is it truly nothing? Terminated would say no. After all, it's already doing quite a lot. It's a stage, a set of rules, a low hum of activity that permits more activity. It's not the philosopher's nothing, not the absence of being, but it may be as close as physics is willing to go. Still, it invites a curious thought. If this is what nothing looks like, then maybe nothing has always been waiting to become something. In the next session, we'll look more closely at one bold proposal, Lawrence Krauss's argument that the universe can come from nothing, and the debates that idea has stirred. But for now, let this rest with you like a thought dissolving into starlight. Demolished is not empty. Fighting is not stit. Takes is a whisper of energy and the rules of chance to begin the story of everything. Let's now turn to one of the more public and provocative voices in the scientific conversation about nothing, physicist Lawrence Krauss. In 2012, Krauss published a book titled A Universe from Nothing, and in it he made a bold claim that modern physics, not philosophy, not theology, but physics, could explain how the universe came into being from nothing. Position it was a powerful idea and a controversial one. At its heart, Krauss's argument draws from all the elements we've explored: quantum field theory, vacuum fluctuations, and the idea that empty space is never truly empty. In his view, the vacuum isn't a placeholder, it's an active participant in the story of creation, a restless field of possibilities governed by known laws. And if those laws are real, if they are fundamental, stable, and universal, then Krauss argues that something coming from nothing is not only possible, it's inevitable. According to this view, the universe began not because something acted upon nothing, but because the vacuum, governed by quantum mechanics, could not help but fluctuate. And with enough fluctuations, given the right conditions, entire universes could spontaneously emerge. Krauss calls this nothing, but many of his critics, especially philosophers and theologians, disagree, because the nothing he describes is still a very structured thing. It has laws, it has fields, it contains potential. It is, in essence, a something, a deeply stripped down something perhaps, but something nonetheless. Flooding with quantum mechanics, critics argue, you've already imported a great deal of structure into the picture. You've already assumed a kind of backdrop, a quantum vacuum, a field of possibility, a canvas that allows for change. Punished, and that's not nothing. Not in the philosophical sense, not in the absolute sense. This difference between what physicists mean by nothing and what philosophers or metaphysicians mean sits at the heart of much of the debate. It's not always a disagreement about facts, it's often a disagreement about definitions. It may not matter that the vacuum has laws. He might say, if this structure naturally exists, and it leads to universes, then that's all we need. We don't have to ask where the laws came from, any more than we ask why math works. They just are. But to others, that answer feels incomplete, because laws are still laws, and laws that always exist, even in a vacuum, may themselves require an explanation. Where did they come from? Why do they have the form they do? Why is there a vacuum at all? Those questions take us beyond physics and into the soft realm of metaphysics, where meaning becomes slippery and certainty fades into mist. Still, Krauss's work serves a valuable purpose. It invites us to see the vacuum not as a passive absence, but as an energetic possibility space, a medium from which, under the right conditions, a universe can arise, not because it's willed into being, but because the rules of quantum mechanics make emergence inevitable. And maybe that's enough. Maybe we don't need a why, only a how. Maybe the nothing that births a cosmos is strange and rich and unstable, and that's just what it is. Or maybe, as others suggest, the real mystery isn't how the universe arose from this quantum nothing, but how this particular version of physics, the one with these particular laws, came to exist at all. Perhaps there are many kinds of vacuum, many possible laws, many kinds of nothing, each with its own flavour, its own potential, its own gentle path toward something. In the next session, we'll explore that idea more directly, the notion that nothing may be unstable, that it cannot stay nothing for long, that nothing, left alone, may naturally become something. But for now, hold this thought gently in your mind. Nothing is not the end of a question. Perhaps it is only the beginning of one. We've followed nothing through many masks. The philosopher's silence, the physicist's vacuum, the quantum field's gentle hum. And now we arrive at a curious idea, one that seems backward at first, yet may be the key to everything. Prohibited isn't stable, like a rock sitting on the ground or a calm sea at dawn, but unstable in the sense that it cannot stay nothing. That, left to its own devices, it naturally becomes something, not by being pushed, not by being nudged, but because doing so is the most likely outcome, even for emptiness. World, this sort of behaviour is everywhere. Particles decay, fields shift, energies tunnel. Systems do not remain fixed in the lowest possible state. They change. Even the most seemingly secure arrangements are, deep down, teetering on the edge of transformation. Look at a quiet example. Imagine a marble sitting at the top of a smooth hill. It seems still, perfectly balanced, nothing happening. But the tiniest breeze, too small to even name, can send it rolling, not because something broke the rules, but because the position it occupied wasn't truly secure. It was a false equilibrium, a waiting game. Gratuitments believe that the quantum vacuum, the closest thing we have to nothing, might be like that marble. Seemingly still, but full of buried tension, a delicate false vacuum, with lower states of energy possible elsewhere. In this view, the vacuum is not perfectly empty, but perched in a kind of temporary balance. And if that balance shifts, even slightly, a quantum tunneling event could occur, a fluctuation, a fall. And from that fall, something new might emerge, like a bubble expanding, filled with space, time, and matter. A universe. Ubiquitous, this is the idea behind vacuum instability. That what we call nothing may be more like a false calm, a pause rather than a stopping point, and that universes might arise not from outside intervention, but from the natural progression of quantum systems doing what they always do, changing. Blinked. Now imagine this on a grand scale. What if there are many different kinds of vacua? What if each has its own laws, its own physics, its own possibility? And what if these vacua can shift from one to another, like a landscape of hills and valleys, each point a different kind of nothing, each one waiting to become something new? This is part of what physicists mean when they talk about the multiverse, a vast space of possible vacua, each one a little different, some empty, some full, some like our own, most perhaps completely alien. And maybe, in that vast terrain, some kinds of nothing are so unstable that they must birth a universe, not as a miracle, but as a consequence of their own structure. Threads, if so, then the question changes. Minimized, well, why is there something rather than nothing? Quantum mechanics are real. If they're baked into the nature of being, then it may be that nothing, as we imagine it, is simply not a sustainable condition. Not the resting state of reality, but a fleeting threshold, a whisper that becomes a word, a pause that becomes a pulse, a vacuum that cannot stay quiet. Of course, these ideas are still speculative. No one has observed a vacuum decaying into a universe. No one has mapped the hills and valleys of the multiverse. These are models, metaphors, equations. But they point to a gentle, persistent truth, that what we call nothing may always have been on its way to something. And perhaps that's the most natural thing of all. Art of our journey will explore what all of this means, how science and imagination walk the fine line between knowing and wondering. But for now, let your thoughts drift softly into the idea that becoming may be more fundamental than being, and that even the quietest silence cannot help but stir. Let's return to a moment we visited before, a moment so brief, so small and so foundational that it hardly feels real. The moment of inflation, when the universe in its first breath expanded not gradually but exponentially, faster than the speed of light, from something smaller than a proton to something vast. It was not a gentle stretching, it was a surge, a brief flash of unimaginable growth that set the stage for everything that followed. And yet, as sudden and dramatic as it sounds, the idea of inflation was born from a very quiet problem. Physicist Alan Guth was thinking about puzzles in the standard Big Bang model. Tiny inconsistencies, like why the universe looks so smooth in every direction, or why space appears flat rather than curved. In a traditional ply, hadn't been enough time for regions of the universe now billions of light years apart to coordinate, to equalize temperature and density. They should have developed differently, and yet they hadn't. Guth's insight was simple but profound. What if there had been time, but in a very different way? Verse underwent a brief period of extraordinary expansion, an inflationary phase that stretched out any irregularities and made the cosmos look smooth, flat, and uniform. What if, in less than a trillionth of a second, the universe grew so vast that all we now observe came from a single, well-connected patch? The theory was elegant. It explained the uniformity, it explained the flatness, it even made testable predictions, like tiny fluctuations in the cosmic microwave background, which we have since observed with precision. Inflation come from? Where things grow strange again. According to the model, inflation was triggered by a quantum field, often called the inflaton field, which held the universe in a high-energy state. While in this state, the universe expanded exponentially. Eventually the field decayed, its energy transformed into particles and radiation, and the hot Big Bang began. Stabilize is sometimes called reheating, a soft name for the moment when the inflating vacuum gave way to the familiar universe of matter, light, and gravity. But here's the quiet wonder at the heart of it all. That first tiny patch, the seed of everything, may have been no larger than a quantum fluctuation. A bump in the field, a ripple in the void, a momentary imbalance in the nothingness. It didn't require matter, it didn't require direction, just energy, latent, restless, guided by quantum rules that said, this could happen. And once it did, inflation took over. That ripple became space, that twitch became time, that brief flicker became billions of galaxies. The universe, according to this model, could have originated from a space no larger than a single subatomic particle. Non-existent, and that's not poetic exaggeration, it's math. Xiaomieri, Theory continues to evolve, and many variants exist. But the core idea that a quantum fluctuation amplified by inflation gave rise to the universe we now observe remains one of the most compelling narratives in cosmology. It's not the final word, but it's a quiet marvel, a story in which the laws of physics, with no guiding hand, allow a universe to bloom from a quantum seed. In the next session, we'll follow that idea even further into a stranger possibility. What if inflation doesn't just happen once, but continues endlessly? What if universes are budding off all the time, each in its own expanding bubble? For now, just rest with this image, flooring a universe born not from grandeur, but from a flicker. Os that began, not with thunder, but with a whisper from the quantum sea. Let's imagine the universe again, not as a single firework, one and done, but as a field of dandelions releasing puff after puff into the breeze. Each one a world, a reality, a separate cosmos. This is the strange and beautiful picture drawn by the theory of eternal inflation. You'll remember from the last session that inflation was a period of extremely rapid expansion, fueled by a high-energy quantum field. And, in the standard model, inflation eventually ends. The field decays, its energy transforms into matter and radiation, and the hot Big Bang begins. That's the birth of our universe. But what if inflation doesn't end everywhere at once? This field doesn't decay all at once like a light being switched off. Instead, it's more like popcorn kernels in a microwave, each one bursting open at its own moment, while the rest continue to heat and swell. This means that in some regions, inflation ends and a bubble universe forms. Inside that bubble, the laws of physics become stable and stars, galaxies, and life might eventually take shape. But outside that bubble, inflation continues. Space keeps expanding, stretching faster than light and creating more opportunities for new bubbles to emerge. Each bubble could be enormous. Each one could be a full-fledged universe just like ours, or entirely different. Some might have more dimensions, some might lack gravity, some might burn out in moments while others unfold for billions of years. And the process never stops. As long as there's any part of the inflating field still expanding, new bubbles will keep appearing. The inflation doesn't slow down, it accelerates, because the space outside the bubbles keeps stretching. The result is a vast and ever-growing cosmic foam, a multiverse of bubbles floating in a sea of eternal expansion. Our universe would be just one such bubble, and we'd be tucked quietly inside, unaware of the others. It sounds like science fiction, but it emerges naturally from the mathematics of inflation. Quantum fluctuations ensure that while inflation ends in some places, it never ends everywhere. There's always more space being created, more vacuum energy to drive it, more chances for new beginnings. Of course, we can't see these other bubbles. The space between them grows so quickly that light from one can never reach another. Each universe is sealed off by the expansion itself, isolated by the very speed of creation. But the implications are profound. In this view, the Big Bang wasn't the beginning of everything. It was the beginning of our patch, a local event in a much larger, endlessly blossoming landscape. And here's where things get even more curious. In different bubbles, the properties of physics might vary. Constants like the strength of gravity, the mass of the electron, or the speed of light might take on different values. This leads to the idea of the anthropic principle, the notion that we find ourselves in a universe with just the right conditions for life, because universes with other conditions simply don't support observers like us. It's a quiet, controversial thought, that our universe might not be finely tuned by design, but merely selected by survival. Whether or not theta inflation shifts the frame, it changes our place in the cosmos from the universe to a universe. Not less special, just part of something wider, a meadow of beginnings, not a single flower. In the next session, we'll explore that meadow more directly, the full idea of the multiverse in its many forms, not just from inflation, but from quantum mechanics, string theory, and even pure mathematics. Your thoughts drift like seeds on the wind. Climb, perhaps the universe never truly stops beginning. Perhaps the story of something from nothing is written again and again across an eternal page. Take a deep breath and picture yourself floating in the night sky. Not above Earth or even the Milky Way, but beyond all of it, beyond our universe, beyond what space and time usually mean. And now imagine that what you see is not one universe, but many, an infinite tapestry, a cosmic archipelago, countless self-contained worlds, each sealed in its own logic, its own rules, its own beginning. The multiverse idea. It's not a single theory, but rather a family of models, each one proposing that our universe is just one of many. Some versions emerge from cosmic inflation, others from quantum physics, still others from string theory, mathematics, or pure speculation, but all of them share a central idea. What we call the universe may not be the whole of existence. Let's walk gently through a few of the possibilities. Breached, there's the cosmological multiverse, the one we touched on in the last session. In eternal inflation, space never stops expanding. It spawns bubble universes, one after another, forever. Our universe is just one bubble in this vast, foamy structure. Each bubble may have its own constants, particles, and physics. Cabbage, we step into the quantum world. Ambiguous standard quantum mechanics, particles don't follow a single path. They exist in a superposition, many states at once, until observed. But what if all those possibilities are real? What if, when a particle could go left or right, the universe splits, and both outcomes happen? This is the many worlds interpretation of quantum mechanics. It suggests that every quantum event spawns a branching of realities, an uncountable forest of parallel universes where every possible history plays out. In one, you turn left. In another, you stay home. In yet another, the stars never formed. Then there's the string theory multiverse. In string theory, the fundamental units of reality aren't particles, but tiny vibrating strings. These strings exist in 10 or 11 dimensions, far beyond the 3 we move through and the one we call time. And the equations of string theory allow for an enormous number of possible configurations, sometimes estimated at 10 to the power 500 different vacuum states. Each configuration could correspond to a different universe, with its own geometry, particles, and forces. Some of these might look a little like ours, most would not. Fiberglass. There's the mathematical multiverse, an idea proposed by physicist Max Tegmark. He suggests that if every consistent mathematical structure exists in some sense, then every possible universe that can be described by math is real in its own way. Ours is just one among an infinite number of logically possible realities. At first, these ideas sound extravagant, like science fiction made mathematical. But here's the quiet twist. We didn't invent them to be dramatic. They emerged from attempts to solve real problems in physics. They weren't dreamed up for wonder. They came from the equations, from the logic of theories we already use to describe the universe around us. We don't know if any of these multiverse models are true. We may never be able to observe the other universes directly. They lie beyond our cosmic horizon, unreachable even by light. But their presence in our models forces us to reconsider what a beginning really means. In a multiverse, there may be no single creation event, no universal clock, no absolute origin, just local beginnings, bubbles inflating, branches splitting, strings vibrating, numbers unfolding, each one a story that starts in its own peculiar way. For Rudgo and we are one such story. In the next session, we'll explore an idea that stretches even further, brain cosmology, which suggests our universe may be a kind of surface floating in a higher dimensional space. Sparkling for now, just let this thought drift across your mind. What perhaps there is no everything. Only ever more somethings, beginning quietly, again and again, beyond what we can see. Let's step now into a picture that's harder to visualize, but no less beautiful. Imagine that everything you know, stars, galaxies, time, the wind on your face, the curve of thought itself, exists not in a vast, empty, three-dimensional space, but on a kind of floating surface, another sheet, a membrane, a rind. And beyond that brain, more dimensions, higher spaces, realities layered not outward like bubbles, but above, below, or beside, in directions we cannot point to because we do not live in them. This is the idea at the heart of brain cosmology, a concept born from string theory, one of the most ambitious attempts to unify the forces of nature into a single mathematical framework. Series theory proposes that all particles are not point-like dots, but tiny, vibrating strings. Their different vibrations give rise to mass, charge, and behavior, like musical notes played on a cosmic violin. But for the math to work, these strings need more room than our familiar four-dimensional space-time. They need 10 or sometimes 11 dimensions. Where are these extra dimensions? Some may be tightly curled up, so small that we can't detect them. But others may be vast, and we may be confined to just a portion of them. In brain cosmology, our universe is a three-dimensional brain, a kind of floating sheet embedded in a higher dimensional space, sometimes called the bulk. All the particles and forces we know, electromagnetism, light, atoms, are stuck to this brain, like ink on paper. They can't move off it. But gravity, perhaps, can. His model leaks into the bulk. It's diluted, spread thin across extra dimensions, which could help explain why gravity is so much weaker than the other forces. But brains aren't just theoretical scaffolding. In some models, our universe began when two brains collided, peacefully to two vast sheets, floating silently through higher dimensional space. When they touch, even slightly, the energy of that collision can trigger a big bang. Not a bang from a point, but from a sudden overlap of surfaces. A transfer of motion and heat that ignites a new cosmos. This is the essence of the ekpyrotic model, a version of cosmology where time didn't begin with the Big Bang, but where the bang was a fiery rebirth from a pre-existing state. The brains move, they pass, they touch, and from their embrace, a universe is born. Go further, suggesting this is cyclical, that brains collide, bounce, separate, and then return, again and again, across cosmic epochs. Each time they meet, a new universe begins. Ours may not be the first, it may not be the last. These are strange ideas, hard to picture, but not hard to admire, because they remind us that space might be deeper than it looks, that our universe might not be alone, not even be living on a cosmic surface we can never see the edges of. In the next session, we'll explore those bouncing models more closely, universes that don't begin and end, but rise and fall like tides. But for now, let this possibility linger in your thoughts. That what we call the universe may be only one layer, a membrane, flirting, waiting, becoming. Let's pause and imagine time not as a straight road but as a loop, a slow circle, a breath that moves in and out again and again. Now, place the universe in that breath. This is the central idea behind cyclic models of cosmology, that the universe didn't begin once and for all, but begins repeatedly. It expands, evolves, fades, and then begins again. Not with a new Big Bang, but with a bounce. Passengers go back further than you might expect. In the early 20th century, even Albert Einstein considered a cyclic universe, one that expands for a while under the force of momentum, then slows down under gravity's pull and contracts again. Eventually, the contraction leads to a bounce and the cycle starts over. At the time, it was more a philosophical musing than a testable model, but in recent decades, new tools, new equations, and new physics have breathed life back into the idea. One modern version is the ekpyrotic model, which we mentioned in the last session. In it, our universe exists on a brain that occasionally collides with another brain in a higher dimensional space. Each collision sets off a burst of energy, a rebirth. The universe expands. Then, over vast timescales, it slows, smooths out, and prepares for the next collision. Another approach comes from the work of Roger Penrose, a Nobel-winning physicist who proposed a model called conformal cyclic cosmology. In this view, the universe expands forever, but the far future and the very beginning might look surprisingly similar. As the universe stretches and cools, matter decays, black holes evaporate, and all that remains is pure structureless radiation. Time in that empty future loses its meaning, just as it did at the Big Bang. Penrose suggests that we can glue these two states together. The remote future of one universe becomes the Big Bang of the next. A new cycle begins, not from collapse, but from forgetting, from erasure, a cosmic amnesia that clears the stage for a new beginning. These cyclic models are bold. They invite us to see the universe not as a one-time event, but as a rhythm, a heartbeat of expansion and return, a song that plays again, not identically but thematically, each verse a variation, each cosmos a new interpretation. But they also raise questions. Buckley, does anything carry over from one cycle to the next? Are the laws of physics preserved? Could something, some trace, some whisper, survive the bounce? Some theories say yes, others say no. Some say the universe forgets entirely, resetting every constant and dimension. Others suggest that structures or even patterns in the cosmic background radiation might bear the fingerprint of an earlier round. Racked far, we don't know, but we are looking. Telescopes scan the sky for hints, subtle asymmetries, recurring patterns, low-level echoes of an earlier time. And if we never find such signs, the idea leaves a gentle impression. Time at the deepest level may not be linear, that the cosmos does not race toward an end, but circles quietly through change. Though what seems final, heat death, entropy, dissolution, might be only a transition, a door closing softly behind one world, while another begins to breathe. Session will explore how one radical theory, loop quantum gravity, proposes that time itself is not fundamental but emergent, that perhaps the universe didn't come from something at all, but simply became. But for now, let this quiet possibility rest beside you. Submerged, the universe may not be a sentence, with a beginning and an end. Repeating, rising, returning. Close your eyes and try to imagine. No time, no ticking clocks, no before, no after, no unfoldingness that doesn't even know it's still. It's not easy. Our minds are made of motion stitched together by memories and expectations. We live inside time. To remove it feels like pulling the thread that holds everything together. Boldest theories of modern physics, loop quantum gravity. Time may not be fundamental at all. It may not have been there at the beginning because there may not have been a beginning in the usual sense. Let's take it gently. Loop quantum gravity is an attempt to reconcile two great frameworks, general relativity and quantum mechanics. Each one works beautifully on its own, but together they clash. One is smooth, the other fuzzy. One describes space-time as a curved continuum. The other insists that everything, energy, matter, motion, comes in discrete packets. LQG takes this conflict seriously. It proposes that space itself is quantized, made up of tiny, indivisible units like the pixels on your screen. But not just two-dimensional pixels, little chunks of volume. Cubes of space so small you could fit 1 billion trillion of them into the width of a single atom. Then so is quantine. Loop quantum gravity, time doesn't flow continuously. It ticks, not like a watch, but like a landscape made of steps, not a ramp. And before those steps, there may be nothing, or rather, no meaningful sense of before. This leads to a powerful possibility, that the Big Bang wasn't a point of infinite density, a singularity, but a bounce, a bridge, a moment where a previous quantum state governed by LQG transitioned into the expanding universe we now see. This is sometimes called the Big Bounce. In this model, the universe contracts down to a tiny scale, not a point, and then re-expands. But during that transition, the classical idea of time may vanish entirely. There's no before, there's no explosion. There's just a change in geometry, one state shifting into another through a timeless corridor we cannot see, cannot experience, cannot truly imagine. At the core of this is a radical shift. Time is not a backdrop. It's not the stage on which physics plays out. In LQG, time is a feature that emerges when space becomes complex enough to host change. Time comes after structure, not before. It's like music emerging from the strings of a violin. Only once the instrument is built, only once tension and vibration are possible. Without the instrument, the melody does not exist. And so in this view, the early universe was a kind of silent string. It did not unfold. It did not wait. It simply was, until it wasn't. This doesn't mean time is an illusion. It means that it's contextual, like temperature or pressure. It emerges when you have enough complexity, enough relationship between things to allow for sequence, cause, and memory. And if time can emerge, it can also disappear. In black holes, in the far future, in the quantum foams where space itself flickers in and out of focus. These are deep waters. Much remains unproven. Loop quantum gravity is still developing, still being refined, but its quiet implications are enormous. That maybe we shouldn't ask what came before the universe. Maybe we should ask what had to exist before time could begin. And maybe the answer is not a thing, not a force, not even a moment, but a change in the shape of possibility itself. In our final session of this part, we'll reflect on the limits of what we can ever know, on the edge where science meets silence and questions become poetry. But for now, let your thoughts drift like echoes in a timeless sea. Not has a before. Not everything needs one, and sometimes beginnings begin only when time remembers how to flow. There comes a point in any journey where the road disappears, not because it ends, but because it fades into mist. This is where we now stand, with all the models, theories, and mathematical dreams spread out behind us. Inflation, bounces, brains, loops, foam, fields. So many ways of saying maybe this is how it began. So many ways of reaching toward the moment when nothing gave way to something. And yet, even now, something quiet lingers in the air. We might not ever know. Not for certain. Not completely. Truths lie beyond the reach of measurement. Some questions reach so far back, so deep into the fabric of existence, that the light they once gave off has long since faded, if it was ever there at all. In physics, we talk about the cosmic horizon, the limit to how far we can see. Because the universe is only so old, light has only had so long to travel, and beyond that radius, we cannot look. Not with telescopes, not with equations, not with the tools of empirical science. Some models, like the multiverse, might predict things we can never observe. Other theories, like loop quantum gravity, describe conditions so far removed from our current reality that testing them directly may be forever out of reach. This isn't a failure of science. It's the shape of reality itself. We live in a universe governed by laws, but bounded by limits. And those limits are not just out there, in the stars. They're in us, in our language, our imagination, our need for stories that have a beginning, a middle, and an end. But what if the universe doesn't work that way? Forest beginning is the wrong kind of word. What if the question isn't what caused the universe, but what is a cause, when time itself is still learning to exist? Science, at its best, is humble. It doesn't promise absolute answers. It promises models, approximations, ideas that work, for now. And sometimes, those ideas are breathtakingly accurate. They let us send probes to Saturn, decode the genome, build tools that can see galaxies 13 billion years away. But other times, science must sit quietly and say, we don't know yet. Maybe we never will. That's not a sign to give up. It's a sign to wonder more gently, to recognize that mystery isn't a flaw in the system. It's a feature of consciousness, a space where thought can breathe, a quiet invitation to listen rather than solve. Flooring philosophers call this epistemic humility, the idea that knowing has limits, and that wisdom begins where certainty ends. It doesn't mean we stop exploring. It means we explore with reverence. Discharge. We can say that the universe began, as far as we can tell, with a rapid expansion from a dense, hot state. We've uncovered so far are both elegant and astonishing. And beyond that, perhaps we rest, not in ignorance, but in awe. Because maybe the greatest miracle isn't that we can explain everything, it's that for a brief moment, on one small planet, a species arose that looked into the darkness and asked, how did anything begin at all? And if the answer is always just out of reach, if the final page remains unwritten, then that too is part of the beauty. In the next part of our journey, we'll return to the human scale, to how all this science, this silence, this wondering about nothing shapes how we see ourselves, our lives, our place in the quiet cosmos. But for now, let this moment settle like a sigh. Uns do not end in answers. They end in wonder, and that is enough. Let's begin here. Not with space, or stars, or gravity, but with something much closer. Your mouth. Or more precisely, your words. Because long before we had telescopes or theories, we had language. We had breath and sound strung into patterns to describe the world around us. And those patterns, those words, are still the tools we use to think. But language is not neutral, it shapes how we see. And when we try to describe something as slippery as nothing, language, so helpful in daily life, begins to fail us. Gently. Consider how we speak. Every sentence needs a subject and a verb. Something must do something. The apple falls. The wind blows. The universe began. Even silence is framed by action. Something must be there, must act, must change. Now try to describe nothing. Not silence, not darkness, but the absence of even the possibility of experience. You might say, there was nothing. But look again, the sentence sneaks in a subject. There was nothing. A place, a container, a frame in which the absence sits. Or nothing existed. Again, existence is a verb, a being, a presence. To even speak the word nothing, we must treat it as if it were a thing, and in doing so, we've already lost the thread. This is not just a poetic puzzle, it's a deep philosophical tension. Can we describe non-being without turning it into being? Can we point at absence without imagining a space in which that absence occurs? The ancient Greeks puzzled over this, so did Indian philosophers, so do theoretical physicists today. Every attempt to describe the absence of something ends up describing a kind of presence, a shadow shaped like an object. Even logic, our most precise tool for reasoning, struggles here. In classical logic, statements are either true or false. Things either exist or they don't. But when we try to apply that neat framework to the concept of nothing, contradictions arise. If we say, nothing exists, do we mean that nothingness exists? And if it does, isn't it something? This is why nothing resists language. It sits at the edge of grammar and reason. It refuses to be held in the hand of a sentence. It slips between our thoughts like mist through fingers. Minimized, we keep trying. To go about nothing is not just a scientific question, it's a human question. It arises from our desire to understand beginnings, to frame the infinite within the finite, to give shape to the formless so we can carry it in words. But words, for all their beauty, are shaped by our experience, and we do not experience non-being. We live in a world of things, shapes, colours, textures, durations. Our speech is moulded by what is, not by what isn't. So perhaps our difficulty with nothing is not a failure of imagination, it's a side effect of existence. Beck, we are something, we live in something. Into true nothingness is always a little blurred. In the next session, we'll follow this thread deeper into the illusion of cause and effect, and how our minds shaped by language and motion insist on finding explanations, even when nature may offer none. But for now, let your thoughts settle. Sometimes the most honest answer isn't an explanation, a quiet pause completed.
It feels so natural, doesn't it?
The way one thing leads to another, the way morning follows night, footsteps follow footsteps, and questions follow from the events that came before. This happened, and so that happened. The match struck, so the fire burned. Unresolved, so the sky brightened. You woke up, so the day began. Citing this gentle unfolding of cause and effect is the rhythm by which we live. It comforts us, gives shape to our memories, lets us trace the lines of our lives backward and forward, like threads in a tapestry. But what if this rhythm is an illusion? Disjoint exactly, but a local habit, a pattern our minds impose on a deeper, stranger reality. Usality works beautifully. It helps us cross the street, boil water, explain why the plant wilts if we forget to water it. But when we step beyond the human scale, into the quantum realm, or the earliest moments of the universe, cause and effect begin to lose their clarity. In quantum mechanics, for instance, events don't unfold in tidy chains. A particle may behave as if it has no definite path until you measure it. Two particles, once entangled, can affect each other instantly across space with no signal between them. These are not violations of physics, they are predictions of it. And they have been tested again and again. Pledged there's general relativity, where time bends and warps depending on gravity, where simultaneity breaks down, where what happens before in one frame of reference might happen after in another. Even our own brains, finely tuned as they are, sometimes reverse cause and effect under pressure. In experiments, people can experience a sense of agency. I chose that, even when the choice has already been made subconsciously. The mind patches over the sequence, painting a neat story after the fact. Reopen out that our sense of causality may be less about physics and more about narrative. We are storytellers by nature. We need to link events. It's how we survive. If you hear a rustle in the grass, your brain immediately constructs a chain. Rustle, predator, danger. You don't need to know, you just need to react. Hamstring has favoured those who assume causes, those who fill in blanks, those who look at the stars and ask, who lit these? But cause and effect, as we know them, may be emergent features, something that appears only when a system becomes large and stable enough to track change over time. Timetable, there may be no fixed sequence, just probabilities, entanglements, and patterns that only make sense once enough complexity arises to host a clock. And when we ask what caused the universe, we may be pressing a question that no longer applies. If time itself began with the Big Bang, or emerged later from deeper laws, then asking what caused it may be like asking what's north of the North Pole. A valid-sounding question, but one that dissolves under closer scrutiny.
So why do we keep asking? Because our minds are wired that way, because our language is full of verbs, because when something moves, we reach instinctively for a reason, because a world with causes feels safer than one without. But maybe the universe is not a story. Maybe it's a structure, one in which causes, effects, and time itself bloom like flowers on a deeper tree, beautiful, fragrant, but not the roots. Slashing in the next session, we'll explore the source of this narrative hunger, how our minds evolved to seek objects and intentions, and how that shapes the way we think about nothing, beginnings, and the cosmos itself. But for now, let your thoughts rest gently on this. Sometimes the question, what caused this, is really just a soft way of saying, I want to understand why I'm here.
Close your eyes for a moment and picture the world around you. Chances are what comes to mind isn't a haze of abstract forces or statistical fields. It's objects. A tree, a cup, a face, a path, maybe even a beginning, a middle, and an end. This is how we think, how we've always thought, in things and in stories. And it's not because we're silly or unimaginative, it's because we're animals shaped by eons of survival in a world made of danger, motion, and decisions. A world where predators lurk, food runs out, storms arrive, and children cry. Trembling in such a world, we needed to notice patterns, to assign meaning, to connect dots, even when no line was there. That rustle in the tall grass might be the wind, or it might be something with teeth. To Traley, became exquisitely sensitive to agency, to things that move with purpose, and even more so, to narrative, to events that follow one another in a meaningful order, not just what happened, but why. This evolutionary gift made us deeply empathetic. It also made us wonderfully paranoid. And it's still with us. When we look at the stars, we don't just see hot gas. Our minds search for faces, constellations, stories in the dark. When lightning strikes, we wonder who sent it. When we stumble, we sometimes whisper, that happened for a reason, even if no one is listening. So when we ask why is there something rather than nothing, we're not just posing a philosophical question. We're reaching for a character or a cause or a sequence that makes sense in the way a story does.
We imagine beginnings, climaxes, consequences. We think of existence as something that had to start, and probably for a reason. Either wrong nor foolish. It's human. This is our means we come to cosmology with deeply ingrained expectations, ones shaped more by the savannah than the stars. We expect events to be linear. We expect causes to be local. We expect nothing to be a kind of empty box, waiting to be filled. Pledged, we expect the universe to make sense the way a story makes sense, where every piece plays a role and every ending reveals a truth. That work like that, flooring may not be more like a structure than a story, more like a vast web than a timeline. Things happen, yes, but not always in a way that satisfies the instincts we evolved to chase prey, protect children, or soothe each other by the fire. Even the way we learn reflects this bias. Think of how children ask questions, over and over. Why? Why does the sun rise? Why do we sleep? Why do I exist? The questions spiral until they land, often on the ultimate one. Who made everything? It's a beautiful instinct. It reveals curiosity, vulnerability, and awe. Bunk again, but it also shows that we're wired to expect that everything is made, that everything is part of a tale with a teller. And when we carry that instinct into science, we must do so
Gently, knowing that some truths may not be characters in a story, but quiet relationships in a deeper, stranger logic. That doesn't mean we stop wondering. It just means we learn to hold our metaphors loosely. In more Russian, we'll try something especially difficult, imagining what it means for the universe to be timeless, and how our narrative minds struggle to enter a space where sequence no longer holds. But for now, just breathe and let this idea settle. Flooring. You think in stories. You dream in stories. But the universe may not, and that's okay. Let's try something strange together. Try to imagine no time, no ticking clock, before and no after. Not even stillness, because stillness assumes a contrast to motion. Not even silence, because silence implies the absence of sound. Not even waiting, because waiting belongs to time. Just timelessness. Already the mind begins to reach for familiar shapes. It wants to picture a black space or a frozen moment, or an endless pause. But all of these are metaphors rooted in time. They carry the echo of before and after, the sense of something halted or stretched. And that's the challenge. Our entire experience is built on sequence. From the firing of neurons in your brain, to the beating of your heart, to the rise and fall of your breath. You are a symphony of time. Every thought, every sentence, every dream unfolds in order. Even the feeling of now is just a delicate balance between memory and prediction. Position to think at all is to move from one mental state to another. So when we try to think about timelessness, we are like fish trying to imagine the absence of water. Not because we're incapable, but because every concept we have swims inside that sea. And yet, in physics, timelessness isn't just poetic. It's serious. Club of quantum gravity, like the Wheeler-DeWitt equation, describe the entire universe as a timeless structure. Not something that moves or evolves, but something that simply is. In these models, the universe doesn't pass through states. It exists as a whole, a block of possibilities, with time emerging only when an observer experiences relationships between parts. Think of it like this. Imagine a book. All its pages already exist. Every chapter, every sentence, already written. But when you read it, the story seems to unfold. You turn one page, then another. Events seem to happen, but the book itself isn't changing. It simply is. Chung physicists believe the universe may be like that. A vast four-dimensional structure, in which time is not an engine moving things forward, but a direction within the landscape. You don't need a beginning or an end. You only need a viewpoint. Projectors, this doesn't mean we're trapped in fate. It means that the passage of time may be an illusion created by consciousness, by the way we step through the book, one line at a time. An experience, hints of timelessness appear. Moments of deep meditation, the feeling of being completely absorbed in a task.
the strange elasticity of time in dreams, where hours pass in minutes or stretch indefinitely. These are glimpses, not of literal timelessness, but of how fragile our sense of time truly is. Unmistaking about the origin of the universe, we often ask, what came before? But if time itself emerged with the universe, or within it, then before may not mean anything. It may be like asking what's south of the South Pole.
Until you realise it points beyond the edges of the map. And so we return, gently, to the idea that some things can't be visualised, not because they're mystical, but because our minds evolved to picture moving things in changing spaces. And timelessness is not that. It isn't a void, or a pause, or a room with no clocks. It's something else entirely, something quiet, something still, something that doesn't need a when to be. In the next session, we'll explore how we try to reach toward these impossibilities anyway, through metaphor, through image and story, through the soft language of symbol. But for now, let your thoughts drift outside the frame of moments. Clang truths do not unfold. Flashback. We've wandered through time, across fields of quantum foam, and into the dark quiet of timelessness. And at every turn, when our minds met something too vast, too small, or too strange to picture, we reached for metaphor. This isn't a weakness, it's a gift. Metaphor is how we make the impossible touchable, how we dress the unknown in familiar clothes. We say the universe expands, like dough rising in the oven. We say particles decay, like fruit going soft. We say light travels, like a child on a long road. But none of these are literal. Light doesn't walk. Dough doesn't fill galaxies. And the early universe was not really a bang. Still, these metaphors help. They give us a way in, a place to start. They act as soft scaffolding, allowing us to build understanding before the deeper, stranger truths are ready to stand on their own. Even the Big Bang itself, that famous term, is a metaphor, coined in fact as a joke by Fred Hoyle, who didn't believe in the idea at the time. He imagined it as a sudden explosive moment, even though, as we now know, the bang was not an explosion in space, but the rapid expansion of space. No fireball bursting into the void, just the stretching of reality itself. Still, the image stuck. It gave people something to picture, a way to hold something otherwise ungraspable. This power of metaphor. When we say the universe has a fabric, we don't mean it's made of cloth. But the image of a stretched sheet helps us understand how gravity bends space. When we say time is a river, we don't mean it flows like water. But the idea helps us feel the directionality, the pull, the sense of movement. When we describe quantum fields as seething, or virtual particles as popping in and out, we're not speaking physics, we're speaking poetry. Carefully shaped poetry, designed to make sense of math that defies the senses. Without these metaphors, much of modern science would remain locked behind symbols, elegant, accurate, but unintelligible to the human imagination. So we paint the unknown. We say the early universe was a seed. We say black holes swallow light. We say the cosmos has a horizon, a gentle bridge between the mind and the math. But we must also be careful. Peacefully. Don't just illuminate, they distort. Every image brings shadows. Every model simplifies. And sometimes, when a metaphor works too well, we forget that it's not the thing itself. Bilingual is not actually a balloon expanding into nothing. Blazing is not actually a path we walk down. And nothingness is not actually a box waiting to be filled. The danger isn't in using metaphors, it's in mistaking them for literal truth. They are tools, not truths. Temporary stepping stones on the way to deeper understanding. Still, what choice do we have? We are finite minds trying to... So we reach for seeds, for stories, for stars being born.
We speak of the birth of time, the death of a particle, the dance of fields. And through those phrases, the cosmos becomes a little more knowable, a little more tender. In the next session, we'll lean even more deeply into that tenderness, into the humility that comes from not knowing, from standing at the edge of reason and choosing not frustration, but peace. But for now, let this thought rest with you. Metaphor is how we sing to the universe when we cannot explain it. It is the poetry of approximation. And sometimes, it's the only language we have. Somewhere in the quiet between equations and stars, there's a truth often whispered but rarely celebrated. Science doesn't know everything, and more importantly, it doesn't have to. From the outside, science might seem like a collection of facts, neatly filed answers to the mysteries of the universe. But from within it feels more like walking through a forest at night, lantern in hand, lighting only a few feet at a time. Each step brings clarity, each question answered gives rise to two more. This is not a flaw, it is the essence of science. Science is a method, and I don't know, yet. It tests, refines, admits error and improves. It's built not on certainty, but on humility. Crimson that humility has shaped our view of the cosmos in beautiful, often humbling ways. Camouflage, when we thought Earth was the centre of everything, that the stars moved around us, that the heavens were perfect, unchanging and orderly. Then came Galileo, peering through a simple telescope and seeing moons orbiting Jupiter, imperfections on the sun, craters on the moon. The cosmos was not built for us after all. It was wilder, deeper and stranger. Later, Newton gave us a universe of precise laws, gravity, inertia, motion. For a while it seemed everything could be predicted, like a great celestial clock. Einstein bent space and time with relativity, and soon after quantum mechanics shattered the idea of a predictable universe altogether, replacing certainty with probability and paradox. At each turn, science let go of old answers. It revised its story. It said, quietly and bravely, "We were wrong." This is humility not as weakness but as strength, as clarity, the willingness to say, this explanation works for now, but we remain open to more. Perpendicular. We stand again on the edge of the unknown. We don't yet know what dark matter is. We don't yet understand the full nature of dark energy. We don't know what lies inside a black hole, and we don't know how or if the universe truly began. Stabilize. There are models, there are breathtaking ideas, but there are also boundaries, places where our measurements run out, where our tools fall silent, where our metaphors turn back. And in those places, science doesn't fill in the gap with comfort. It leaves the question open, it waits, it watches. It invites us to think harder, look deeper, and ask better. This approach is more than a method. It's a philosophy of careful wonder. Minimized, because while science can't explain everything, it can explain something. And that something grows, step by step, discovery by discovery. Bisbolier, it's a quiet resistance to certainty, a gentle rebellion against dogma, a way of honouring not just what we know, but how much we still don't. That often demands quick answers, this patience is rare and beautiful. In the final session of this part, we'll reflect on what all this made.
Unknowing leaves behind, on the feeling that sometimes rises up when questions outlast answers, a feeling not of frustration, but of awe. But for now, rest in the thought that science, at its best, is not a monument, but a campfire, a place where we gather in the dark, compare notes, share questions, and pass the light gently forward. After all the questions, the models, the metaphors and the mysteries, after walking through cosmic beginnings, quantum vacuums and timeless realms, something gentle remains. Not an equation, not a theory, not a solution tied neatly with a bow, but something deeper, something quieter, a kind of awe. As confusion, it is not the frustration of an unanswered question, it's the pause after the question when the mind lets go of needing to solve and simply marvels that the question can even be asked. Tangled. It's what you feel when you look up at the night sky and forget, for a moment, where your thoughts end and the stars begin. Pem, it's the stillness that settles over you when you realise you are made of the same particles as the firelight, the oceans, and the dust that once drifted between stars. Awe is not an argument, it doesn't seek to convince. It simply says, this is beautiful, and I do not fully understand it, and that's okay. In some ways, awe is the most honest response to the idea of nothing.
Because nothing, true, complete nothingness, doesn't fit into the tidy drawers of logic or language. It's too wide for that, too quiet, too patient. And so, we return again and again to this soft, humbling space, not because we'll ever fully explain it, but because we're drawn to it, like tide to shore, like breath to silence. Plunged, poets, children and philosophers all touch this feeling in their own way. Confiscated Carl Sagan once said, "We are a way for the cosmos to know itself." Maybe that's all we need to be, not decoders of all mysteries, but quiet witnesses to the fact that there are mysteries at all. Flooring, there is something about standing at the edge of understanding and choosing not fear, but reverence, not frustration, but stillness. Blinked, if nothing can give rise to something, if the fabric of reality itself can emerge from quantum shimmerings, or from a timeless geometry, or from a bounce, or from a fluctuation, then perhaps we do not need to pull apart every thread. Sit beneath the stars, feeling your own heartbeat, and to whisper how astonishing this is, that anything exists at all. And that whisper, soft and fragile and ancient, is the answer, not because it explains, but because it accepts. Because awe doesn't close the book, it keeps the pages turning. While it holds the lantern, the next part of our journey will ease into the wind down, the final reflection. We'll gather the thoughts we've wandered through and let them settle like dust at the end of a long quiet day. But for now, let awe hold you. Schizophrene, let it be your lullaby. Because sometimes wonder is not what comes after knowledge. Blindness, it is what begins before it. Imagine standing at the edge of a vast plain watching the sun rise. The horizon glows and a new day begins. It feels natural, this sense of a starting point, a moment when before becomes after. For many years the Big Bang has held that same place in our cosmic imagination. The ultimate sunrise, the beginning of everything, including time itself. But what does that mean? It's tempting to think of the Big Bang as an explosion in space, a kind of celestial firework bursting into a waiting void. But that image, though vivid, is not quite right. Defending to general relativity and our current cosmological models, the Big Bang wasn't an explosion in space. It was the expansion of space. More precisely, it was the beginning of space-time, a moment when not only space, but also time itself emerged. In this view, asking what came before the Big Bang is like asking what's north of the North Pole. It sounds like a reasonable question, but it quietly assumes a framework that doesn't exist beyond that point. Imprisoned in this picture didn't tick forward from a past into the Big Bang. The Big Bang was the origin of the ticking. Before it, there was no before. Prosecutes the equations of general relativity predict that, if you follow the expanding universe backward far enough, density and temperature increase without bound. Eventually you arrive at a singularity, a point of infinite density where the laws of physics as we know them break down. It's not a literal point in space, but a breakdown in our description of reality. Marks the edge of our understanding. It's not necessarily a real place or a real moment, but a signal that our tools, the models, the math, the assumptions, no longer apply. Still, we can say this. Experienced began with the Big Bang. It's the reference point from which all cosmic history flows. Stars forming, galaxies swirling, you sitting quietly with this thought. Flooding then the idea of a 13.8 billion-year-old universe only makes sense if time has meaning from that moment forward. We count from the Big Bang, not before. Prosecutes in everyday life, it's hard to picture something beginning without a before. Every beginning we know, a story, a song, a sunrise, has a lead-up, a context, a first note that follows a pause. But in cosmology, the Big Bang is different. It is not the first note in a melody, it is the creation of music itself. It is not a chapter in a story, it is the opening of the book. And so in one of the most profound shifts in human understanding, we've come to see that time may have a boundary, not a wall we can touch, but a soft edge where our usual concepts lose meaning. This isn't a place we can visit, it's not something you could point to out in space. It's a feature of the universe's structure, a reminder that our everyday intuitions don't always scale up to the cosmic level. In the next session, we'll discipline it. Pause and ask more carefully. What does it actually mean for time to begin? Can something with no before be said to start at all? And how does that affect how we understand our place within this unfolding cosmos? But for now, sit gently with this quiet truth. There may never have been a moment before the first moment. Time did not arise in time. It is the frame in which everything else arises. And it began, not with a bang, but with a beginning. Let's linger for a moment on a very peculiar phrase, the beginning of time. Maybe in textbooks, maybe in documentaries, maybe whispered beneath the stars, And on the surface it feels simple enough. Time had to start somewhere, doesn't everything? But when you begin to turn the phrase over in your mind, gently and slowly the questions emerge. What does it mean for time itself to have a beginning? We know what it's like when something begins in time. A candle is lit, a river starts to flow, a thought takes shape. All of these events happen after something else. They unfold within a timeline, with before giving way to after. Say time itself began, we lose that scaffolding. There is no before for it to emerge from, no hidden place where it waited, curled up like a seed in soil, no countdown before the clock begins. It's like trying to imagine the first second with no zero on the other side. Philosophers have wrestled with this puzzle for centuries. Some have argued that time must be eternal, that it can't begin because to begin is already to assume time. Others have said that beginnings don't require before, only a boundary, a place where a concept stops making sense. Just as a line can have an edge, time may have an origin that doesn't imply a prior moment. In physics, this problem becomes sharper. If time and space are interwoven, as general relativity tells us, then the birth of the universe wasn't just the birth of where things are, it was the birth of when they happen. And so the Big Bang isn't just the start of matter or light or stars, it's the beginning of chronology itself. Floringer's view, time is not a hallway stretching off into an infinite past. It's more like a room with walls you can't pass through, and the beginning of time is simply one of those walls. But we're not used to this kind of boundary. When we imagine the end of a road, we think we can step off it. When we see the edge of a map, we wonder what's beyond. When we watch a story unfold, we assume a prologue. So we bring those instincts to the universe, asking, what happened before the Big Bang? What caused it? Where did it come from? But these questions may be like trying to dig a hole in a shadow. They rest on assumptions, particularly the assumption that time is always there, stretching endlessly in both directions. Yet in cosmology, time is conditional. It requires a framework. It may emerge from something deeper, like space, like entropy, like the state of the universe itself. It could even be relational, arising only when change is possible, when events can be compared. No events, no time. No relationships, no flow. This illusion, the beginning of time, may not mean a fiery instant bursting out of nothing. It may simply mean the point at which time becomes meaningful. Before that, if before even applies, there was no clock, no sequence, no unfolding, just the absence of those concepts. In the next session, we'll shift perspectives again, looking at time not as a river we drift through, but as a shape, a dimension, a structure in space-time's geometry, as described by relativity. For now, breathe gently and rest in this. Connection not have started in anything. It may simply have started. Setbacks from somewhere, not from something, but as the condition by which all other somethings can appear. If you step outside on a crisp night and look up, it's easy to imagine space as a vast emptiness, an invisible container in which stars are pinned, planets drift and galaxies swirl. Time, by contrast, feels different. Less like a place, more like a movement. It ticks, it flows, it carries us along moment by moment, never letting us stop or step back. But in Einstein's theory of relativity, that intuitive difference between space and time begins to blur. Time is not separate from space. They are woven together into a single fabric called space-time. And in this fabric, time is not a river, it's a direction. Let's pause here gently. This idea is easy to say, but harder to feel. And you walk north or south, you move through space. Your location changes, but you remain you. According to relativity, you are also always moving through time, just by existing, even when you're standing still. Regulate your movement through space affects your movement through time. The faster you go through space, the slower time moves for you. This isn't metaphor. It's been measured in satellites, in particle accelerators, even in clocks flown on aeroplanes. It's called time dilation, and it reveals a universe where the passage of time depends on your frame of motion. And there's more. Gravity bends space-time, and time itself ticks more slowly near massive objects. This means a clock on a mountain runs faster than one at sea level. You and your wristwatch are already feeling the stretching of time, even if just by fractions of a second. So what does this sing of beginnings? Foreground, it means that time is not a fixed background against which events occur. It's part of the stage itself, a structural dimension. In many ways, relativity invites us to see time as a kind of landscape, a four-dimensional geometry in which everything that has happened, is happening, and will happen simply exists. This is known as the block universe view. Imagine the universe as a giant loaf of bread. Each slice is a now, from the perspective of a particular observer. You and I might see different slices depending on where we're standing and how fast we're moving. But the whole loaf exists at once. Past, present, and future are all baked in. From within the loaf we feel time flow, because we experience events in sequence. But from outside, from the perspective of physics, that flow may be an illusion. There is no universal now, no cosmic metronome ticking in sync for all. Every observer carries their own clock, their own slicing of reality. This makes the idea of a universal beginning subtler. If the universe is a four-dimensional structure, then the beginning of time is not a distant moment receding into the past. It is a corner of the geometry, a boundary condition in the shape of everything. You don't reach it by moving backward. You reach it by understanding how the fabric itself is built. In the next session, we'll visit one of the smallest, earliest slices of that structure, the Planck epoch, the tiniest fraction of a second after the Big Bang, where space-time trembles and our understanding begins to blur. But for now, let your thoughts settle into this new shape. Flames is not a stream pulling us forward. It is a dimension we walk through, frame by frame. And the universe may be not a movie, but a map. Now let's narrow our focus, not across light years, but across the smallest sliver of time the universe has ever known. The Planck epoch. It's a name that sounds gentle, almost polite, but what it describes is anything but simple. This epoch refers to the first 10 sames the 14 seconds after the Big Bang, a number so small it barely feels like a moment at all. It's the Planck time, named after physicist Max Planck, who helped lay the foundation for quantum theory. It represents the shortest meaningful unit of time in physics. Beyond this threshold, our understanding dissolves. Forfeit a very early time. It's a limit, a wall in our knowledge, where the familiar equations of general relativity and the wild rules of quantum mechanics clash with full force. In the first fraction of a second after the Big Bang, the universe was unimaginably dense and hot. All the fundamental forces, gravity, electromagnetism, the strong and weak nuclear forces, may have been united into one. Space and time themselves were not yet clearly shaped. They were blurred, frothing, uncertain. Here the concept of before and after begins to flicker. Time, as a smooth and flowing dimension, may not yet have settled into its rhythm. We do not have a working theory that fully describes what happened during the Planck epoch. That's because we don't yet have a theory that unifies quantum mechanics, which governs the very small, and general relativity, which governs the very large. The universe at that moment, we need both. This is the domain of quantum gravity, a field still in its infancy, still building its bridges. Loop quantum gravity and string theory both offer possible glimpses into this era, but nothing is settled. Nothing is certain. Left with a space on the cosmic map marked gently with, "Here our equations fail." But this isn't a failure. It's a kind of humility. A boundary that reminds us that even in our most powerful models, there are questions not yet ready to be answered. Still, we can say some things. Universe expanded rapidly from this early state. A period known as inflation may have begun just after the Planck time. Tiny fluctuations in energy, seeded during this epoch, may have grown into the galaxies we see today. The structure of everything, the stars, the trees, even you, may have its roots in quantum flickers during this unknowable moment. But the moment itself remains hidden. like the first page of a book that's been sealed shut. We know the story begins there, but not what's written. And so, cosmologists and physicists return again and again to this edge, not to pry it open in frustration, but to honour it, to test its boundaries, to imagine new mathematics, new metaphors, new tools to see what cannot yet be seen. I dare represent toward the first instant, toward the moment when time became time. In the next session, we'll explore one of the most profound ideas born from this mystery, that perhaps time itself did not start in the Planck epoch, but emerged from something timeless. But for now, rest gently with this. There is a moment so small, so early, so unknowable, had no space to move. And yet from it came everything. It's one of the most delicate questions we can ask. Not just what came before the universe, but whether before ever meant anything at all. In our everyday experience, everything seems to rise from something. A thought follows a memory, a tree grows from a seed, even silence follows sound. But what if the universe did not come from anything in time? What if it came from a state where time itself did not yet exist? Let's pause with that thought. Not just the absence of things, but the absence of when things could happen. This is where modern physics gently turns mystical, not because it tries to be, but because it arrives at a place where meaning bends, just slightly, out of reach. Some models, like loop quantum gravity, propose that time is not a built-in feature of reality, but something that emerges when conditions allow it, like a melody that only arises once the violin is tuned. Before that, there's no song, only strings, only tension, only potential. In these models, the early universe may not have unfolded through time. It may have been a kind of timeless quantum structure, what some call a quantum foam or a pre-geometric phase. No ticking, no unfolding, just relationships, probabilities, the possibility of becoming. And from that, something shifted. Not because a clock struck 0, but because the system changed. A symmetry broke, a balance tipped, and suddenly time was not just possible, it was meaningful. The universe began to have direction, not before, not after, but within. To help feel this, imagine a still lake at dawn. The surface is calm, featureless, timeless. Now, a ripple begins. A single motion disturbs the symmetry, and suddenly you can point to moments, before the ripple, after the ripple. A history emerges, not from an external clock, but from the appearance of change itself. This is what some physicists believe happened at the very first moment of our cosmos. The universe transitioned from a timeless state into a state where time could be measured. Not a fireworks show, but a phase change, like water freezing into ice, or mist condensing into a drop. Seizing in this transition, time is born, not as a thing, but as a pattern, as an ordering of events that can now be counted, compared, remembered. This doesn't mean the timeless state was a place we could visit. It wasn't a realm hidden before the universe. It was a condition, a kind of primal stillness without narrative, a pause that had never been a play. Lumming maybe we can't ever access it, not directly, because the moment time begins, the memory of timelessness disappears, like waking from a dream you can't describe. You know you were somewhere, but the language doesn't follow you back. Some models, like those inspired by quantum cosmology, even suggest the transition from timelessness to time may be inevitable, because if time is not eternal, if it had a moment of becoming, then what do we mean when we ask how the universe began? Are we seeking a cause, or simply trying to understand the shape of the transition? In the next session, we'll explore how cosmologists frame this question using boundary conditions, ways of defining the shape of the universe, not with edges, but with elegant curves and constraints. But for now, Feel the quiet wonder of this idea, that time may have emerged, like a ripple on still water, that the universe didn't begin in time, paltry. Picture a circle. It has no beginning, no end, no sharp corners, no place where you can say, here is where it starts. It just turns, quietly and continuously. Every point leads naturally into the next. Now imagine if time were shaped more like that. When we talk about the beginning of the universe, we often picture an edge, a frontier where nothingness ends and something begins. A hard border, a line in the sand. But many cosmologists are starting to think that the universe may not have a boundary at all, not in space, not in time, not the way we usually imagine. The oversight arrived using something called boundary conditions, a mathematical way to define how the universe behaves at its edges, or, if you like, how it behaves in the absence of edges altogether. On Earth, you can walk in a straight line and eventually return to where you started, because Earth is curved. Finite but unbounded, there's no edge to fall off, no end of the road. You can keep walking forever, looping gently over the globe. Now apply that same thinking to time. Flushing it itself is finite, but has no boundary. What if, like the surface of a sphere, the timeline of the universe curves back, not in the sense of looping endlessly, but in the sense of having no hard beginning? This is the heart of no-boundary models in cosmology. Instead of imagining the Big Bang as a point or a wall, these models describe the early universe as a smooth curve, a rounding off of time where the distinction between before and after becomes blurry, like dusk blending into night. In these models, time may gradually emerge from a state that isn't quite time and isn't quite space either. The beginning is not a line, but a slope, a transition, a soft geometry where the laws of physics gently take shape. It's a bit like a hill rising from flat land. There's no sharp border where the hill starts, it simply begins to rise, and before long you're walking upward, even if you can't say precisely when the climb began. Mathematically, these boundary conditions allow physicists to set constraints on the entire shape of the universe, guiding how it evolves without requiring an external cause or a sharp beginning. They are not explanations in the narrative sense, but structures, descriptions of the full loaf of space-time, not just one slice. This kind of thinking helps move us away from the idea of creation as an event and toward creation as a shape, a topology of possibilities. It's hard to picture. Our minds like events. We like causes, fireworks, and moments that mark the start of something new. Not work like a story. It may work like a structure, and its origin may lie not in a bang, but in a smooth curve of possibility rising out of stillness. In the next session, we'll visit one of the most elegant examples of this idea, Stephen Hawking's no-boundary proposal, which imagines the universe as a timeless bubble, curved in on itself like a globe, requiring no edge, no before, no outside. But for now, rest in this. Not all beginnings are bursts, some are roundings, semantics where nothing sharpens into something. Not suddenly, not loudly, just gently.
Now, let's gently arrive at one of the most elegant and perhaps most poetic ideas ever offered about the beginning of the universe. An idea that replaces the hard edge of a beginning with a curve so smooth, so continuous, that the notion of before quietly disappears. This is Stephen Hawking's no-boundary proposal, a model he developed with James Hartle in the 1980s. It's not a story about events, it's a shape, a geometry, a mathematical whisper about how something can begin without starting. Hawking asked, what if time behaves differently near the origin of the universe? In our normal experience, time is like a line. It moves forward step by step, measured in seconds, hours, years. But Hawking suggested that near the very beginning, time may not have existed as we know it. Instead, it may have behaved more like a spatial dimension, something curved and finite, but with no edge. To explain this, he borrowed a concept from quantum mechanics called imaginary time.
It's not imaginary in the sense of made up. It uses a mathematical tool called the imaginary unit, the square root to 1, to describe time in a new way. By rotating time into this abstract direction, Hawking showed that the equations describing the universe could be smoothed out, like the rounded surface of a sphere. Here's the metaphor he often used. Imagine the Earth. It has a north pole. If you're standing there, every direction is south. But there's no boundary at the North Pole. It's not an edge, it's just a smooth curve where all directions meet. No wall, no corner, just a point where the landscape softly turns. Hawking's no-boundary model proposes that the beginning of the universe is like that. Not a singularity, not a wall, not an abrupt start, but a rounded region in space-time. A smooth surface with no edge. And if that's true, then the universe didn't need a cause. It didn't need to emerge from nothingness in the traditional sense, because there wasn't a before. There was just a timeless shape from which time itself unfolded, like a soft bloom opening in a silent field. This doesn't mean the model is complete. There are open questions, technical challenges, and debates in the field. But what makes Hawking's proposal so powerful isn't just the math, it's the gentleness of it. It removes the need for a hard beginning. It erases the demand for a before, and it replaces the mystery of creation with something quietly geometric. A rest, a shape, a smoothness, a universe with no boundary. This idea doesn't answer every question, of course, but it reframes the big one. Not what came before time, but what kind of geometry gave rise to time as we know it. It's a shift from fireworks to flow, from cause to condition, from nothing to form. And that form, curved, continuous and serene, reminds us that sometimes the most profound answers are not found in louder questions, but in simpler curves.
Letting go of the need for a sharp origin, and instead accepting a beginning that simply softens into being. With this, we complete our final part. In our closing wind-down, we'll gently reflect on all we've wandered through, the concept of nothing, the birth of time, the limits of knowledge, and the quiet awe that surrounds it all. But for now, a universe without a hard start, a beginning without a bang, flooding, smooth, silent curve, rounding gently into everything.
Before the first note of a song, there is silence. Before a word is spoken, there is breath. Before a story begins, there is the pause, the hush that holds the possibility of everything that might unfold. And so too, we imagine there might be a kind of quiet that comes before the cosmos. A void not cold or hostile or empty, but waiting, listening, still, nothing. But maybe that's just the best name we have for a kind of invisible expectancy. A poetic place where meaning hasn't arrived yet, but the conditions for meaning are softly being shaped. Throughout this journey, we've explored nothing as a scientific idea, quantum vacuums, pre-geometry, imaginary time. But now, in these final reflections, we return to nothing as something gentler, a shape we can't quite see, but one we feel at the edge of our understanding. In art, in music, even in sleep, we encounter it. A Basho stared at a blank canvas, not just empty space, but a surface heavy with possibility. The poet sits with a quiet page, hearing lines that haven't yet arrived. The sleeper drifts into dreams through a doorway made not of thoughts, but of silence. We live in a world full of noise and motion, but the most meaningful moments often rise from stillness, from pauses, from that breath you take just before saying something true. And maybe the universe began with a moment like that. Not a bang, not a burst, but a gathering, a gentle rounding, a transition from a poetic kind of nothing into the story of stars and light and time. It's tempting to think of nothing as a cold absence, a void that resists imagination. But in many ancient traditions, nothingness isn't feared, it's revered. The Tao speaks of the usefulness of the empty vessel. Zen embraces the silence between thoughts, and mystics have long described God as both fullness and void. There's wisdom in this, because the more we search for a clean definition of nothing, the more it seems to slip away, like mist, or like the moment before waking. Not the absence of everything. Minimized, it's the condition for everything. Like the still air that makes a single violin note audible. Like the blank space that gives a poem its rhythm. Like the silence that makes a lullaby feel like sleep. Next session, we'll ask whether nothing can ever truly be known.
or whether even naming it pulls it into something. But for now, just sit with this. Before your first memory, there was a quiet. Before the first star, there was a darkness. Confined, and maybe before the universe, there was something that wasn't quite nothing. Something more like a pause, blackjack, a breath, islands before the story began.
Let's begin with a paradox so soft it feels almost like a whisper. To describe nothing is to turn it into something. Even now, as we ask, can nothing be known, we're already assigning it shape, weight, a question mark at the end of a sentence. And perhaps that's the quiet truth hidden at the heart of this entire journey. Conflicting, rather, true, total, complete nothingness may not be something we can ever hold in thought. Not because we haven't thought hard enough, but because the very act of thinking requires something. You can't think about a presence to stand outside it. Manslaughter in non-being without being there to imagine it. Even the vacuum in physics, stripped of particles, is still something, a field, a structure, a shimmering web of potential. Even the blank page is a page. Even the silence has a clock ticking somewhere in the room. Conflicting leads many philosophers and physicists to wonder, is nothing just a linguistic illusion, a placeholder for something we can't yet define, or never could? In logic, nothing is often treated as the empty set, the set that contains no elements, but that's still a set. It has structure. It exists within a mathematical system. In physics, the quantum vacuum is as lively as a stage before a play begins. Thus virtual particles bubble in and out. Fields ripple. Space itself carries energy. Even in theology or metaphysics, nothing rarely stays clean. It's often replaced with mystery, spirit, potential, or the infinite. Fallback. In we ask, can nothing be known? We might really be asking a deeper question, in which imagination itself doesn't exist. Breaking because to truly know nothing would require us to erase the observer, to remove all context, all sensation, all categories of meaning, and that gently acknowledge it is the absence of knowing. Still we try, because that's what humans do. We name what we can't touch. We chase shadows with flashlights. We write poems about silence. We explore the idea of nothing not to grasp it completely, but to reach the edge of what we can say. That edge is where the most meaningful things happen. Embraces science meets philosophy. Soviets where logic gives way to awe, where our questions no longer demand answers, but offer companionship in the vastness. So maybe the point isn't to know nothing, but to recognize its boundaries, to accept that some things can't be cornered by thought, that some mysteries are not puzzles but landscapes, meant not to be solved but wandered. We'll walk through the paradoxes we've met along the way, beginnings without time, causes without befores, something from the absence of everything. But for now rest in this quiet conclusion. Maybe nothing cannot be known. Maybe it is not an object of thought, but a mirror showing us the... As we near the end of this long and gentle journey, it's worth pausing to look back. Not with the goal of resolving every question, but simply to marvel at how many of them twist. Twist like a path that folds in on itself. Like a mirror reflecting a mirror. Like a thought that circles quietly until it becomes its own answer and its own question again. Because when we talk about nothing and how the universe began, we find ourselves walking through a forest of paradoxes. Consider this one. In prison, had a beginning, yet there was no before. We say time started with the Big Bang, but started is a word soaked in time. It usually means that something once wasn't and then was. So how can time begin without already being embedded inside time? You count what happened before the first moment. You can do that question. You can see that the churning and which, with your finally, to sis in the side. We can tone what happened before the first moment, to peel the skin off a shadow. The question dissolves the moment it's asked. Here's another. The universe came from nothing, yet that nothing had laws. Quantum fluctuations, vacuum energy, spontaneous appearance, these all sound like nothing, until you realize they rely on a framework, a set of rules, a stage, even if that stage is empty.
So is it really nothing, if it comes with instructions? We're told something can arise from nothing, but then find that our definition of nothing has quietly evolved into something minimal. And then this. Causality feels essential, yet may not be fundamental. Selectively, our minds crave cause and effect. We want to know what triggered what led to what came first. But as we've seen, on the quantum level, or at the beginning of the universe, cause and effect may not apply in any familiar way. Perpendicular itself emerges like time, like space, from deeper rules that don't follow the rhythm of because. We also met the paradox of the observer. To describe nothing, you must observe it. But to observe it, you must exist. And if you exist, it's already something. Even Hawking's no-boundary proposal, elegant as it is, invites a paradox of interpretation. The universe has no edge, yet begins. The start is rounded, smoothed, timeless, but still marks a beginning. It is a model of non-beginnings that still functions as an origin. So we walk among paradoxes, not because we're confused, but because we've wandered to the edge of concepts that were shaped for simpler tasks, for hunting, for surviving, for storytelling by firelight. And now we're using those same tools to talk about time and vacuum and space-time geometry. Of course they bend. Paradox is not a flaw in the model. It's a sign that we've stepped beyond comfort, into places where human intuition is still learning to breathe. Maybe that's the most honest thing we can say about all this. Tavasize the universe may not fit inside a single box, that it may not be a
Tensions. Each one pulling, each one balancing the other. From nothing comes something. From stillness comes time. From unknowing comes the desire to ask again. In the next session, we'll explore why, despite all this slipperiness, we keep asking the question at the heart of it all. Why is there something rather than nothing? But for now, let the paradoxes rest in your mind like slow-moving stars. They don't all need solving. Some were made to be lived with, to be circled gently, like walking paths under the moon.
After all we've explored, the equations, the boundaries, the paradoxes and the silences, you might wonder something simple. Why does this question matter at all? Why do we keep asking what nothing is, or where the universe came from, or whether anything had to begin? It's not because we expect to find a final answer tucked neatly inside a textbook or hidden in a telescope. It's because the question itself does something to us. It opens something. When you ask, why is there something rather than nothing, you're not just asking about atoms and space and time. You're asking about you, about meaning, about existence, about the quiet fact that you're here at all, thinking, breathing, wondering. And that question connects you not just to science, but to every curious mind that has ever tilted upward and asked the same thing. From the earliest myths to modern physics, this question has echoed. The Greeks asked it. So did Buddhist philosophers, medieval theologians, Enlightenment thinkers. And today, cosmologists and quantum theorists still circle it, running experiments, building models, not always to explain nothing, but to see just how deeply structure reaches into silence. Because this is not just a question of facts, it's a question of orientation. It reminds us that the universe didn't have to include anything, yet here it is. Vast, blooming with galaxies, and somehow in one quiet corner, you. Pedestrians, in a world full of noise, goals, errands and screens, this question slows us down. It gives us perspective. Not in the sense of humility as smallness, but humility as wonder. It says, you are part of something that may never fully explain itself. Polluted, and that's not a reason to feel despair, that's a reason to feel alive. This question also invites connection. Conspicuous, because even if we disagree on the details, on God, on physics, on language and math, we often begin with the same breath. Why anything at all? And in that breath, we are no longer strangers. We are fellow travellers, forest holders of a candle in the dark. This question also drives science forward. Pedestrians to explores researchers to explore the limits of the observable,
to build better telescopes, to test deeper theories, to unify the very large and the very small. Not for the sake of trivia, but for the hope of touching the edge of structure itself. And even when we don't find the answer, the question refines us. Humility deepens our sense of mystery, constrained our gaze wide. So no, we may never know exactly what nothing is. We may never step outside time, disperse the moment before the first ripple in the void. But the asking changes us, the wondering slows us, the listing widens us. We may never up so far. The Cambie column T effectifies where the universe. We'll rest with that feeling, not chasing an answer, just letting wonder be enough. For now, remember this: unresolved matter not because they explain, but because they remind you.
Feel. Reinstall. To pause. To breathe. Rencontre of the strange and beautiful fact that anything exists at all. And now, here we are. At the end of this long, slow unfolding, a journey that began with the question, what was nothing before the Big Bang, and gently spiraled through physics, time, quantum foam, boundaries, and the soft flickering mystery of thought itself. We haven't found a final answer. But perhaps we've found something just as precious. A reason to let the question stay open. Because not every mystery exists to be solved. Some exist to be felt, to be held gently, like a stone warmed by the sun. Not examined for every crack, but cherished for the stillness it brings. Quiet wonder isn't flashy, isn't demand a stage or an audience. It whispers, it watches. And when you lean into it, when you let yourself feel the beauty of not knowing, you find a kind of peace that's deeper than certainty. A stillness that welcomes you, not because you understand, but because you were willing to ask. All along this path, we've been circling an idea that's bigger than science or philosophy, or any system of thought. The idea that existence is a miracle, not because it defies rules, but because it exists at all. You are part of a universe that may have no edge, whose time may have risen from timelessness, whose laws may shimmer out of vacuum, and whose beginnings may have no beginning as we imagine it. Gambling, and yet, here you are. Breathing. Listening. Wondering. Maybe the most honest response to all of this is not explanation, but awe. Nigel. Not answers, but presence. The kind of presence you feel in the woods at night, under a sky too large for words. The kind of presence that comes when you stop asking just for facts and start asking for meaning, forbidden, for connection, for stillness. And so, if you're lying in bed right now, letting your thoughts drift like leaves on a quiet stream, know that the question is still with you, not as a burden, but as a companion. It asks for nothing. It promises nothing. And yet, it opens something in you, something that makes room for the stars. Because in the end, to wonder about nothing is also to wonder about everything. Prejudice, and to live in that wonder, without needing it to resolve, is its own kind of wisdom. So let this be your lullaby. The universe may not explain itself. Prisnachina you, even in silence. And sometimes, listening is enough. So here we are, at the quiet edge of it all. You've wandered through the fabric of the cosmos, step by careful step. You've drifted across theories, tiptoed through paradoxes, and stood, softly, at the border of what we can know and what may remain unknowable. Not all questions found answers. Silenced, all were allowed to breathe. We began with a puzzle. What was nothing before the Big Bang? And perhaps in the end we discovered it was never just a question about physics. It was a question about perspective, about humility, about standing beneath the stars and realizing just how vast the silence is, and how beautiful it can be. We explored how space and time may have unfurled together, like a page turning not from one chapter to another, but from blankness into the story itself. We saw that the Big Bang wasn't a bang at all, but a blooming, that time may not stretch forever into a past, but instead gently rise from a place where even before has no meaning. We played with the idea that the universe may not have begun with a cause, or even an event, but with a curve, a soft rounding of space-time that didn't need a sharp start, like the quiet swell of breath before a word is spoken. And we looked into nothing, not as a cold void, but as a mirror, a concept that reflects our limits back to us, that dares us to speak with care, to wonder without rushing in to explain. Throughout this journey, we didn't just gather facts, we gathered a feeling of sitting with mystery, the feeling of breathing at the edge of knowing, the feeling that maybe, sometimes, it's okay not to fill in the silence, because silence is not emptiness, the space where meaning can arrive. In the next and final session, we'll close our eyes with the universe. We'll let the questions go, not because they're answered, but because they've done their work. And we'll let sleep wash over the mind like a soft return to that timeless place. One more quiet breath. The stillness of thought. You've wandered into beginnings that may not begin, breached and found, perhaps, not certainty, but peace. Now let it all drift away. Let the questions settle like dust on an old windowsill, untouched, undisturbed. Let the theories, the paradoxes, the glowing edges of the cosmos soften until they are just gentle echoes in the back of your mind. You don't need to hold them anymore. Safeguard is coming. And sleep is its own kind of mystery. It's a place where time relaxes, where the borders between thoughts blur and dissolve, where your mind steps quietly out of the rhythm of clocks and enters a softer, deeper rhythm, one that isn't measured in seconds, but in size, in warmth, in stillness. Sleep, in its own quiet way, brings you back to something that almost feels like the void we've been exploring. Not a frightening nothingness, but a tender one, a cradle of not knowing, a space where being rests without the need to explain itself. When you sleep, you don't worry about beginnings. You don't need to define time. Balloons, you don't ask where the universe came from. You simply are, held by gravity and breath and the slow, patient rhythm of rest. And maybe, in that state, you come a little closer to the kind of timelessness we've been circling. A moment that isn't counted. A pause that isn't between things, but its own kind of presence. So as you lie there, in your bed, in the quiet corner of your world, know that the universe isn't asking anything of you right now. You don't need to solve it, you don't need to understand it, and that is enough. Forging, if your eyes are still open, you can close them now. If your thoughts are still racing, let them slow. If your heart is still restless, feel the weight of the blankets, the rhythm of your breath, the warmth of being. And as you drift into sleep, take one final gentle thought with you. Bronze, the universe may have begun with a silence, a breath before time, undefeated, a moment where being stirred and softened into motion. Conflicting and now, as you return to your own silence, may you find rest in that same stillness, in the awe of not needing to know, blister only to dream. Good night, fellow traveller. You for sharing this quiet journey. Sleep deeply, and let the mystery keep